friends, programmers, data analytics 2 students, lend me your ears today, for I have a wonderful model to show you. Today, we're going to be talking about principal component analysis. Now, this sounds very fancy, and it is, but I'm going to break it down. I'm going to spend a lot of time going over behind the scenes of how it works and show you like a full example. I found a great example online on YouTube and I kind of based it off of that. I'll leave the link in the description below. But in general, I'm going to just show you how it works. And even if that is a little bit too complex, don't worry, because after that, I'm going to show you how to actually use principal component analysis in Python with scikit-learn. And you'll see that's a piece of cake. Like, you could technically do that without understanding all behind the scenes, but I still want you to show you so that you can appreciate it and better understand what it does and what it's good for. So, what is principal component analysis good for? Okay, well, let's think back to the iris dataset that we had at some point, but also the other datasets like the crypto dataset and whatnot. We had different points, so different sample points that we have, and we had different features for those, right? So the sepal length, sepal width, pedal length, pedal width, or in the case of the crypto, we had different days, and then for each day we had like the buying price, the selling price, and other things that we didn't use, like the percentage of volume and things like that. So when we try to graph these things, we struggled with it, right? We had a hard time basically trying to do that. So like if I went in and, for example, with the crypto data set and I ran it and I graphed it, I would end up with these clunky 3D images, and even then I'm still not able to show all the features because I had more than 3, and even 3-dimensional graphs are already like kind of finicky. You have to be able to manipulate them to like see them better, but it's hard to like understand them. And when you go to 4D, well, at that point you have to have either multiple graphs or you just have to cut away with some of the features when you're graphing, right? And if you do that, you miss on things. You miss on patterns that you might otherwise see, right? And one of the things that you're doing when you're analyzing data is you want to be able to visualize that data for others to be able to understand what you find, and also for you to find new things that you might otherwise miss, right? So the ability to graph things 2-dimensionally, it's like a 2D graph, the XY that we're used to, but still make it a good representation of the data, even when we have more than 2 dimensions, is very, very powerful. And that's one of the things that principal component analysis can help you. Now, is it the solution for all problems, like the be-all, like the go-to thing? No. Principal component analysis will help you in a lot of cases, but it's going to be depending on the data. As we'll see, one of the big things about dimensionality reduction, which is kind of what we're going to be doing, which is, as the name implies, reducing the dimensions. So from something like 10-dimensional feature space into something 2-dimensional that we can graph, is that you really have to find the correct mix of the different features that can allow you to represent it in 2 dimensions, but not miss what each feature's value is. So what do I mean by that? Well, suppose that I had, the following data. I'm graphing it, and I have 2 classes, and they're split like this, 2-dimensional. If I have something like this, and I'm trying to like analyze the data visually, then it's very easy to see that I can separate the data, right? This way. And you saw that with the 4-vector machines, right? And then when I went ahead and said 3D data, suppose that now the data is actually like this. It's not very easy to linearly separate, but if we were to look at the third feature, that was like the depth, then maybe looking at this like from the side, so this is like a side view, all the x's will be here and all the circles will be there, and we can draw some kind of plane that can linearly separate them, right? And that was like the kernel trick and all those things, going to a higher like dimension. So here we kind of want to do the other way around. We still want to keep it 2-dimensional, but we want to take advantage of the fact that one of the features, which in this case is this depth feature, like Z, would actually help us to like linearly separate the data. So we want to sort of make it a new sort of combined feature that takes a little bit from other features. And then when you graph that sort of brand new sort of combo feature, can visually represent both this left side and this right side. And so you might be like, whoa, that's like some dark magic. And frankly, if you don't know how Pca works, yes, it does feel like dark magic, but that's why I'm going to show you how it works, right? Because what it's doing is it's basically taking, let's say, 10 features and then reducing that to 2 features, but still taking the important things of them. So perhaps there are 2 features out of the 10 that are like really important. So it's going to give a heavy weight to those when it's graphing it in 2D, but it's still going to try to retain as much as it can from the other ones. Okay? So that's really the goal behind using Pca. And that's to reduce the dimensionality, but still be able to keep the uniqueness of the multiple features. And so what I want is that if I graph this 2-dimensionally, it would look like this. If I graphed it 3-dimensionally, I would be able to see the depth. But Pca is going to give me like a brand new graph that will separate things like this. The dots may look a little bit different, but I'm still going to be able to detect that pattern that I otherwise wouldn't see unless I did it in 3D. And now think about that with like a 10th D example. So maybe only in the 10th dimension can I actually see this sort of separation in a hyperplane. Well, with principal component analysis, I can still graph it in 2D and see that separation. So then I can run my clustering and detect patterns and things like that, okay? So that's one of the main goals of principal component analysis, is to be able to graph those things. So I want to be able to graph this in 2D, but still keep that sort of patterns that I can detect. So maybe like this is a cluster of pieces, this is another cluster, and so on. That's kind of the main goal. The other useful thing about principal component analysis is that when you're doing machine learning, we talked about this in the last video, right? We talked about the curse of dimensionality. The more features you have, the more data you need to really support those features so that you don't draw yourself into a corner of overfitting. And so it's not always a good idea to like throw like 1,000 features at a model when you only have like 1,000 data points, because like imagine that each data point is like heavily biased on one feature and they're all unique. So then you're not going to go anywhere with that data set, because your model is just going to like overfit basically because each feature is really meant for one data point. Then it's going to literally say, well, whenever the feature is this much, it's going to be this answer, and it'll work because it's like super overfit, but it's going to be useless when you test it with additional data, right? So it's not a good idea to have that many features, but you also don't just want to throw them away sometimes, because you're like, well, yeah, but like I kind of want them. I mean, sure, I wish I had more data, but I'm kind of stuck in this situation. So like, what do I do? And also, how do you pick between which feature is actually important, right? Like, how do I know of all the features I have, which ones I should throw away and which ones I should keep? Well, principal component analysis is also very useful for that, because when you're doing your little graphs to be able to like to reduce the dimension, you can see the recipe that the Pca model used to create that. So the model can say like, hey, I use features 20 and 25 because they were the ones that actually were better at separating the data. So they were like more important. You can see that, and then you can be like, oh, okay, well, maybe I should keep those features when I'm training my model and then throw away some of the ones that are like least important, because you can see that too. And that way, your model is still going to perform good, because you know that those are the features that are actually that actually have a visible difference between the different inputs, different samples that you have, and allows you to train the model better and remove the useless features that are like noise. So Pca is very good at that. It allows you to reduce your number of features. You could train with the Pca's actual output, but I'll leave you to explore doing that. But really, those are the two main things are going to be dimensionality reduction for graphing. So you can graph and visualize higher dimensional data, which is a very powerful thing. And second, trying to figure out which features are good and which ones are not. Now, principal component analysis, again, doesn't always work for all data. Imagine a data set that basically has all features. Like imagine you have like 5 features and they're all equally as important. Then you really can't do much to reduce the dimensionality of that. You can still grab the PCA like components, which that's what they're called. I was trying to avoid using that, but they're called components, the new sort of X and Y that you create out of the original features. So you can still grab the components and like visually find patterns, but it won't help you in the case of trying to say like, well, which feature can I remove to reduce the number of features I feed to my machine learning model? Because PCA is going to be like, yeah, well, they're all the same. So like, they're all as important. So in that case, it's not going to be good. So it's only good for machine learning, like model-wise, if the PCA detects like and says, hey, these features are more important, these are not as important. If that's the case, then awesome. Like you won because you can now pick the ones that are important. But if PCA comes back and tells you like, hey, they're all equally as important, then you're kind of stuck at square one. But at the same time, at least you know they're equally important. So that's another useful thing. So I mean, even in the fact that you failed at something, failing at it by telling you that they're equally important, does actually teach you something about the data, right? It teaches you like, oh, okay, well, maybe I can try approaching this in a different way. There are also other sort of dimensionality reduction and clustering sort of techniques that you can do to data. There's UMaps and there's discriminant analysis and other things that are pretty cool. Maybe someday we'll get around to making a video of those, depending on how things go. But I think principal component analysis is one of the most basic ones that you should know. It's a completely new sort of group of algorithms that we haven't sort of looked at. And so maybe we're interested in talking about unsupervised learning. So I was like, hey, this seems kind of fitting. Okay, so like I said, I actually went down and just drew a bunch of stuff and wrote a bunch of stuff because otherwise this video would take me hours. So really, I'm just going to like, it'll be almost like a pseudo slide because I have a bunch of stuff written here. And then I'll just talk about it. And then the sooner I go through this, the sooner I can actually get to showing you some code. So I will leave a link on the description below of what I used. I looked around the internet and I said, you know, what is the best way to show PCA? And I found a really cool video from StatQuest. And so this is based off of that. So I encourage you to go watch that video. Unfortunately, that video and its follow-up video are for our programming language, not for Python. So, you know, I had to make my own Python stuff. But at least the explanation kind of comes a lot from there. So, yeah. I mean, there's tons of videos online, but I think that one was the one that I personally was like, hey, this is neat. So, okay. So, again, to make sure that you see what we're trying to do is like we have something like this that has 4 dimensions and we're going to reduce it to 2 dimensions so that we can graph, you know, 4D graph, pretty hard to do, I think. 2D graph, pretty easy to not just do, but also to analyze afterward, visualize. So this is the goal. As you can see, these are called principal components. And yeah, that's what we want. Okay, so let's go ahead and start. The first thing that you want to do when you are computing this, obviously, you know, if you're doing something on a 10 dimension, what you would do is you just follow the programmatic steps of doing this. And there's a lot of linear algebra and matrices involved. I don't want to show you that because you'll panic and you will not understand the basic idea. And again, I want you to understand the basic idea, not really because I expect you to replicate this on your own, but really just so you can get an idea of what is happening. So when you use the machine learning library, you know like how this even came to be, you know, versus like thinking it's just dark magic, okay? So what I'm really going to be doing right now is I'm going to be taking what is basically 2-dimensional data, all right? And you might be saying like, well, why are you just taking 2-dimensional data and making like a 2D graph from that? Well, because I'm taking 2-dimensional data and different sample points for that, okay? So really you can think of like, there's 3 things involved here. There's an x-axis, there's a y-axis, and then there's also the number of points, okay? So you have these 6 points. Now, you can obviously see from this that the points are sort of clustered separately, right? So like already here, I would be like, well, this is a cluster and this is a cluster, right? Sure. But again, this is only because it's a very basic example from a two-dimensional space to, we're just going from 2D to 2D. But again, this would be the same thing you would do for like an nth dimensional space, and then things would get a little fancier, okay? So don't just discredit it at the end of this, be like, why did we do all this? No, it's really because I want to show you how it works. And then you can think about doing this for a higher dimension, which is what you would actually be doing when you're doing it with a real data set. Okay? So again, that's what we start with. We have this 6 points right here. Okay? And the first thing that I want to do with this, so I'm going to do a bunch of little math steps basically. And the first thing is I want to find out where the center of the data is, including Euclidean distance wise. Okay? So I go ahead and measure all my points, you know, get the average of that and get the center of that data that I'm looking at, okay? Now, what would be the center if you were looking at a higher dimensional space? Well, if it was a 3D one, the center would be on 3 dimensions, right? And then what about when you go to 4 dimensions? Well, it might be difficult to like draw that, but mathematically you would do the same thing. You'd still use Euclidean distance, so you just have, you know, like four variables that you'd have to work in instead of 2 variables in this case, okay? So you can see how this would extend to any dimension. It's just that it's easy to see with 2 dimensions, okay? So once you find the center of that, you want to shift the graph, so shift all your points by whatever the offset is of the center. So basically you're dragging things down like this, okay? So I'm dragging the points down so they're right on the center, okay? So now the average is on the center. Now, the reason why we're doing this will come clear later on, but it does make the computations a lot easier, okay? So once you've shifted to the center, I want you to draw a line. So think about like linear regression, right? When you're doing linear regression, what you're doing is you're trying to find the line that best fits the data, right? And so when you do that, you have to first draw an initial line with some random weights and then start computing what the ideal weights for that would be. But you have to start somewhere. So it's the same thing here. We're trying to find a best fitting line essentially. So we're trying to do a form of regression, which you know how to do, right? You know a lot of ways to do it, but we're going to do sort of a different way here. And so I just went ahead and picked the most random line possible. Well, it's not the most random, I guess, but it doesn't really matter, and you'll see why. Because no matter what you start with, you're still going to work your way to the to what is the best fitting line. Okay, so that's going to be your red line. Now, what I want to do is I want to rotate this line until again I find the best fitting line. And this is the only difference in like normally with regression, when you're trying to find a fitting line, you can shift it down or shift it up and so on, right? It doesn't have to go through the origin or the center. In this case, though, that's going to be the extra requirement. I do want to keep it going through the origin, which is basically the average of the data, right? So that's the difference from like regression to this. Okay? So in this case, this is kind of what I want to come up with. Okay, I want to be able to have the line go right through as many points as possible, right? So to have it fit better. But let's better specify what it means for a line to fit well, right? With regression, you know that, but here we're going to be looking at distances. So let's talk about what that means. When I say the line fits the best, I'm talking about minimizing the distance from the line to the points, okay? So here I have back to the first line, the random line that I came up with. And as you can see, I have my 6 points, and the way that I'm figuring out whether this line fits well or not is let's look at this point here. I take this point and I measure the distance from this point to where the line is. Now, why am I measuring it like this versus measuring it like this or like this or like this? Well, I want to form a 90-degree angle here. Okay, so I'm looking strictly where it forms a 90-degree angle with the line. That intercept right here, where this is perpendicular, that is the point that I'm measuring the distance from. So like, for example, for this point, I'm not looking here, I'm not looking here, I'm looking here, because again, this is where it forms a 90-degree angle. That's important. Okay, so just a little bit of math that you got to do there to do that. Again, I'm just trying to show you the concept, but I'm sure you could figure out the math to compute that. Okay? And actually, I'm going to show you some trigonometry in a second here. But yeah, so 90-degree angle, okay? That's what you want to do. And so when you measure that for all the points, and you add it all up together, okay? And then that would be what you're trying to minimize, okay? But what we're going to be doing is something a little bit different. So while this would work very fine, so you're trying to just minimize this distance, this is a little bit hard to compute. And so instead, what we can do is, instead of computing this distance here, I'm going to compute the distance that maximizes from the origin to wherever that intercept is. Okay? So whereas here I was trying to measure how I can shorten this, because you can see that in the line that fits like this, the distance is really small. You see that? Look at that distance here versus like this one where it doesn't fit as well. They're bigger, right? So you can see that like making that smaller is what we want. However, it turns out that computationally that's a little bit more work for the computer to do. So instead, what I'm going to try to compute is to maximize this distance. So instead of trying to minimize this distance, I want to maximize this distance. Now, those things are actually equal, but it's a little bit unintuitive to see that. I have another graph that I found online, and I'll leave the reference below, that kind of shows you that, how those distances change. So check this out. It's pretty cool, right? So you can see that when it's the best fitting line, that distance gets decreased, right? Like for example, for this point, this is not fitting too well. You know, this is actually fitting at the worst possible case is when it rotates around the origin, right? So whenever like it's perpendicular, it doesn't fit. But now it's becoming better and better and better and better until ideal point would be in if this specific dot goes through the line. But not all of them can because they're not all lined up, right? Okay, that's cool. Now I want you to notice the distance that this 90-degree angle makes for that point. So it's like right here. Notice how it gets farther away from the origin as it basically touches there as the furthest it is, and then it starts to get closer as the line gets longer until the worst case, which is when it goes to the origin as it's perpendicular right there, right? And then it starts to get closer again. So you can see that as the distance decreases here, it also increases there. So those things are equal. And you can draw triangles to sort of visualize that. Okay, that both of them do the same thing. So here I have the same thing that the GIF showed you, but sort of with a little triangle, all right? So what I have here is the green line is the distance from the origin to the point. And as you can see, this is not a straight line, as in like this is not this. So this is strictly speaking for each point, what the closest path, the shortest path is to the origin, okay? So those are different. Whereas the red line is my current estimation of the best fitting line. So you can see that this makes a right angle, right? You got a little triangle here. And in this triangle, you have this base of the triangle here is the distance from the point to where the intercept would be with your best fitting line that you figured out so far. And then the red here, which goes to the origin, is the other side of this triangle. And then finally, you can think of this as the hypotenuse of the triangle, right? Which is the distance. So you can see that as you get a better fitting line and you reduce this, this also increases, right? And this follows a property, right? So what is this following? Pythagorean theorem, right? So this is following the Pythagorean theorem because you can see that this squared plus this squared is equal to this squared, right? And imagine a scenario where this right here was 0. So this angle right here, this line became 0 because like you just basically were the red line was going right to the dot. Well, in that case, the red line and the green line would be equal, right? So this would be like some like b squared is equal to c squared or something. So you can see that like when that is maximized, that would be the case because in Pythagorean theorem, a squared b squared is equal to c squared, or a squared is plus is equal to b plus c squared, whatever, b squared plus c squared, however you see it. The point is that the biggest line is always going to be this one, right? And then from there, you have these two. And depending on the angle is which one is longer, right? But as this gets shorter, this has to get longer until this becomes equal to this when this is 0, okay? So that's why maximizing works. Here's just another example of like almost maximized. You can see how the green and the red are almost the same, but there's, technically speaking, because this is not 0, still the red one's a little bit shorter than the green one, but it's always going to be it's going to be the longest one of all. And then an example here where it's definitely not maximized, you can see that the green line would essentially become as long as the purple line. So that's worst case scenario, okay? So here I have some sort of key reminders of that the green doesn't change because that was just your distance to the origin. So no matter what you do to the rotating line, the distance from the point to the origin does not change. Purple is going to get smaller as you find a better fitting line, and red gets longer as purple gets smaller, okay? So in theory, here we go, a perfect fit for purple is 0 and the red is equal to the green, okay? So here's that Pythagorean theorem, and this is color coded to what you saw in the line. And you can see a squared plus b squared is equal to c squared. Some people do it as a squared is equal to b squared plus c squared. It doesn't matter which one you go to, they're just variable names, okay? So this Pythagorean theorem property is actually going to be useful. So I thought, if you thought the last time you saw Pythagorean theorem was in high school, well, you were wrong, okay? So like I was saying, minimizing a squared, which is the distance here. So minimizing this distance, oh, I just erased it. It's an effective thing to do, but it's not efficient. It's a lot more efficient to compute b squared, so to maximize the distance. So I want to maximize the red line. And then, of course, when it's maximized, it's because the purple is minimized, right? So both get you the answer, but one of them is easier to do. It's like, imagine trying to say, okay, I want to figure out what 20 times 10 is. And one way to do it is to say, okay, I'm just going to add 20 10 times and then do each of those additions separately, or I can do the multiplication, which is just a one-step process, okay? So like one of them is easier than the other one if you remember your multiplication tables. But if you don't remember them, or let's say the multiplication tables were like a really expensive process for a computer to do, then you would just do the addition, right? So this is kind of the same idea. One of them is easier to compute than the other ones, okay? And so now I'm going to introduce this concept of sum of all squares. So when you go in and actually maximize distances to all of them, you save them. So for each point you have a maximized distance, which we're going to call like d1, d2, all the way to dn for the n number of samples. And what you're going to do is you're going to square all these distances, and that's the number that you're trying to minimize. Now, why are they squared? Why don't I just add them normally? Well, that's because if you see here, some of those distances might be negative and some of them might be positive, right? Because some of these are behind the line and some of them are ahead of the line. And so negatives and positives tend to cancel each other out, which would give you incorrect results as to what the best fitting line is. So by squaring them, we're basically just getting rid of that canceling process happening, okay? So sorry, I got distracted because I still have the spinning thing there. So I was like, that's hypnotizing. So let me just get rid of that. Okay, so yeah. So basically that's why it gets squared essentially. You could do absolute value, but squared just what they decided to do, so that's what we'll do, all right? So, and I have it written there, square so the negatives are not canceled, okay? So again, those distances are what you're seeing here. This is what we're computing. We're trying to compute and maximize those distances. So how do we maximize them? Well, compute them all. All right, you computed them all for one line. Now try rotating the line a little bit, like 1 degree. Compute them again. Is the number bigger or is it smaller? If the number is bigger, it means that you should be going in the other direction. If the number is smaller, that means you're actually getting a better fitting line. So you keep doing that. Eventually, you're spinning, and then, it's like smaller, bigger. And you're like, oh, it's bigger. So that means I probably overshot it. So you go back 1 and it's still smaller. So then you basically found pretty much almost the ideal line, right? So what do you do then? Well, you could decrease your number of increments, and so instead of going 1 degree, you go like ½ degree, or you could just call it a day. You can think of it like your learning rate. You know, what do you do once you sort of hit that local minima? Except here, there is always going to be an optimal fitting line. Like there's never going to be a scenario where there isn't one, because there's only one line that can actually fit the data that would actually give you the best result. Computing that is tricky, you know, but like exact one, because it might be like, you know, to the millionth decimal points, but within certain accuracy, you can compute it. Okay, so that is that's the basic idea of getting that sum of four squares. So rinse and repeat. You know, rotate the line, recompute until it decreases, repeat it until you find the optimal line. Okay, so you just found the optimal line. Congratulations, you're almost there. First big step has been completed now. We have our optimal line. It means that the distances are maximized. So that means that like this is this squared plus 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 this squared is the smallest number you found for a line. Okay, that line has a special name. That line is called the principal component. And in this case, it's principal component 1, because it's the first one that you computed, okay? So it doesn't matter if this is 2 dimensions or 20 dimensions. The first line you compute is the most important one, and it's called principal component 1, okay? And that line, like, remember what the slope of that line is, okay? We're going to come back to talk about the slope. But also understand that when you computed the line, you computed a specific sum of square distances, right? So you have a specific value for D1 and D2, which are these, right? That also has a very important name that I want to talk about. So the sum of the square distances that make that best fitting line, so those D1, D2, D3, so those are called the eigenvalue for principal component 1. Okay, so this eigenvalue name is something that you'll hear when people talk about PCAs, like, what is the eigenvalue of that? What is that? Now you know what it is. All it is adding up all of the distances squared, because remember the negatives. So you add it all up for that fitting line that you did, and that's the eigenvalue, okay? It's a fancy name. You can go look up the history behind the name, eigenvalue, eigenvectors, and all these things. But for now, that's all I'm going to say about what eigenvalue is, okay? So again, the distance is here. Once you've found the ideal line that minimizes these distances, or sorry, that maximize these distances, that combo of numbers, D1, D2, D3, that you have n of them, and n being the number of points that you have, the number of samples, for the best fitting line, you know, the best points that you've found, the best distances, that's your eigenvalue, okay? And there's another terminology. If you take the square root of that number, so like let's say you know, it's like D1 is 1 and D2 is 2. That means 1 squared plus 2 squared, which is 5. You know, 4 plus 1 is 5. So if you only have 2 points in your graph, that would and that was the distances that you computed, then that would mean that your eigenvalue would be 5. And then if you take the square root of that, then we call that the singular value of PC1. Okay, so the square root of the eigenvalue is called the singular value. We'll come back to that at some point. Okay, so again, I want to make sure that we are on the same page. So let's just do like a quick example. So let me just make a graph, and let's put a dot, and let's just say this is a 1, 1. Okay. And then to make my life easy, I'm gonna put another dot here that is at like -2, -2, okay? So suppose that you start out by making your first guess happens to be this line, okay? This line has a slope of basically 2x, right? And of course the ideal line is 1x, but let's just say it's 2x. All right, so let's compute the sum of square distances for this simple example, okay? Let me move this somewhere else. I guess we can do it here. Okay, so if we want to compute the sum of square distances, what we do is we find out where this and this touch, right? And so again, we could minimize those, but we're trying to maximize the distance here. Oh, even the highlight is really thick because we're zoomed in. So this is what we're trying to compute, the pink one, the neon pink or whatever that is, okay? So what is that distance? Well, we could do some Pythagorean fanciness for that, but I'm just going to go ahead and kind of guess it based on the distances here. So this is 2, and then I mean this kind of looks like it's at around. It's kind of like this point here is at about -1, -3. Let's just kind of guess like that's the case, okay? And then we know that the other point is at -2, -2. So, you know, we can just find out the Euclidean distance for that, which for simplification purposes, because I don't feel like doing right now a lot of math, let's just go ahead and say that's a distance of 1, okay? Now, it's less than 1, more than likely, but yeah. Actually, this can't be 2, by the way. This is not 2, this is more than 2, because 2 would be the vertical line like this. So, in fact, if I want to find out what that line is, I can just say 2 squared plus 2 squared, which is 8, right? 4 and 4. And then that is basically equal to that. So technically, the real distance of the line, the black line here, is actually the square root of 8, which is like 2.7 something. Hold on. Let's see, square root of 8. 2.8. So really this is 2.8. Okay? And so, you know, this, if I guess that that's about 1, you know, then I guess this would be about something that gives me the square root of, something that gives me 7 squared, basically. So again, something like let's just say like 2.2 or something, okay? So this could be something approximately that. And then just because this is almost mirrored, then this really should be the same. So, well, I could totally use some trick to figure out the exact values of this. But like I said, I am not interested in really doing that. But this line, the black line up here, that is the square root of 2. Whatever that number is. Because 1 squared plus 1 squared. So, yeah, that was square root of 2. So, yeah, okay. So again, let's just say that this was like some like 1 value here, okay? So just as a guess, again, this is not exact numbers. The only ones that are actually exact right now are this one and this one. But let's just say that that's 1 and 1, okay? So I want to find out what the sum of square distances is. I would add the square of both of them, okay? And oh, and also this one might be like -1 or something, but that's fine. Again, because it gets squared, the negatives get canceled, so that's why you don't even worry about that. So what this equals then is going to be 2, right? So the 2 right there is your current eigenvalue per se. That 2 is the eigenvalue. Now you rotate the line again. So let's say you rotate it again. And so this time when I rotate it, I actually like land right on the line. Or this is a different color. I rotate it. In this case, what is it going to be if we were calculating the minimum distance, we would see that it was 0. But again, we don't do that because it's hard. Instead, we'll calculate the maximum distance, right? So what is the current maximum distance? Well, then it's actually, because it's going, you know, in this very special case, it's going through both points exactly, then we actually have these be the maximum distance. So square root of 8 plus square root of 2, right? Because 2.8, that came from square root of 8. So now what I'm going to do to compute that eigenvalue is I'm going to take square root of 8 squared plus square root of 2 squared, right? So it just basically becomes, that's why I left the square root of 8 and not 2.8, because otherwise I'd have to square 2.8 and be like, So this becomes 10. So you can see how 10 is much bigger than 2, right? So we are maximizing that value. So this is when we maximize it. Because if we go past this, like let's say we go past the line, so like next time we compute it, we try to draw like this line. You can see that this line is going to be not as maximized. Like technically it's going to be like maybe like 2.7, and this is going to be like square root of 2 minus like 0.1 or something, because this is not 0 right here. So therefore this line has to be longer than this one. So this will be shorter. So this will give us like 8 instead of 10. So you can see how the 10 has to be like the biggest value, right? It has to be that we can get. So once we've maximized that, then we can say that that is the best fitting line, which happens to have a slope of 1, right? And the eigenvalue is going to be 10. And then the singular value is just the square root of 10, which where's it at? Here, singular value. So we'll be the square root of 10, okay? So that's like a practical example if you wanted to see with numbers. But again, I wouldn't worry too much about this. Even then, I hand waves how to compute that. But I mean, you can see that computing that is not like trivial. There's a lot of little math operations. And when you're dealing with like tons and tons of features, each feature you got to do all these computations for, find those Euclidean distances, and then also you have to do all these squares. Those numbers add up, and it takes a lot of work and time. So like, you know, you need that multiprocessing power to be able to do this quickly. You know, those tensors and all that. But yeah, anyways, okay. So we've computed the eigenvalue, whether that be for a toy example or our optimal line example that we have there. And now what I want to talk about is the slope of the line, okay? So you saw in my example there, the one that I just did, the slope of the line was 1. In this one, the slope looks less than 1. It's a little bit flatter. So we're just going to kind of say that it's a quarter of a slope. So that means that for every 4 units on the x-axis, it's 1 unit on the y-axis. So I guess 4 and 1, okay? So what does that mean? What does that mean that we have a sort of a small slope versus, or a less steep slope versus the other one where we had a 1 of slope? Well, this is actually going to tell us which variable or which feature is actually more important. So when looking at these two features, if we see the slope is more heavily reliant on one feature, you can think of the line being closer to that axis. So the closer the line, I guess this way. So the closer the line is to the axis, so the more flat it is, the closer it is to the x-axis. Whatever the x-axis feature is a more important feature that you want to keep in your model. If the axis is more steep of the line, if the slope is more steep of the line, so like I guess going from here to here, if the line looked more like this, that would tell me that it's actually more biased, like more important to have the feature on the y-axis. And by the way, picking which one goes on which doesn't matter. You just have to be consistent. So again, I'm not bringing up anything about what these features are in this example. They're just whatever you want them to be. And then you graph them however. So you pick whichever one for X and whichever one for Y. But just be consistent once you pick them. Otherwise, you cause problems. So what does that mean about our example where the slope was 1, 1? Well, this is actually kind of like a bad case scenario because that means that both features are equally as important. Now, in this case, it's just 2 features, so it's not that big of a deal. But if we had something similar to this with 10 features, where like the slope was basically kind of like in the middle of all of them, that would be a scenario where principal component analysis wouldn't really help us a lot because it would basically tell us like, hey, all the features are kind of like just as important-ish. So, but we're not done. We're not done yet. So, but at least at this point, we start to be slightly disappointed. But there's more to be done that can still help us out. Okay? So let's kind of keep going from here. So we saw the slope for this one. So let's forget about this example for now. Let's just stick to the one that I have here, because all the pictures are based on this one. So you can see that the slope is only a quarter. So it's kind of basically telling us that x is 4 times as important as y, right? And you can see that if it was 1 to 1, it would be that x is 1 to 1 to y, so that would be equal ratio. Okay? So again, in this case, larger slope, like I said, would have meant something like this, like with a slope of 3. That would mean that 3 is, I have a 4 here. It's 3 times as important as x. Right? So in this case, always think of it like a fraction. And if it's a whole number, then just make it over 1. Bam, you just made a fraction. So in this case, x is more important. In this case, y is more important, right? If we had data like this. But of course, our data is actually like this, right? So, yep, that's all I said. So comparing these slopes has an actual name, and that name is called linear combination. So the linear combination between both variables. And so just remember that name in case you ever hear it. Okay, but now let's talk about singular value decomposition. Okay, so we already heard what singular value is, right? Because singular value is the square root of the eigenvalue, right? So suppose that we have our principal component, which is that line, the best fitting line. Remember, that's called principal component. And suppose that we have it something like this. Okay, you can see that in this case scenario, obviously when you make your principal component line, it's not going to go through all the periods, all the dots, all the points. Like that would be perfect. But at that point you're just making it. It's just because it's actually the points will make a straight line. But that's never going to happen, right? So suppose that amongst thousands of points that we have, we're looking at one specific point and we're looking at that distance, right? So you can see that the principal component line is the purple one here. So this is where the intercept would be. And then this here, distance, is the distance as part of your eigenvalue. And you can see that we have an x-axis and a y-axis distance here, right? And we can compute those with Pythagorean Theorem, like that, right? So x squared plus y squared is equal to d squared, okay? So let's go ahead and plug in some numbers here so that you can see that, okay? So suppose that, that x is equal to 4 and y is equal to 2, okay? Now, how do I know that? Because that means that this point right here, the coordinates of this are 4, 2, right? That means 4, 2, right? So that's how I'm kind of guessing that. All right, but again, the numbers don't matter. I just wanted to show you an example with numbers. So suppose that x is equal to 4 and y is equal to 2, okay? So if I want to compute what d is equal to, then I can just take 4 squared plus 2 squared, which is 16 plus 4 and 20, and then that's equal to d squared, so just take the square root of 20, right? So that's square root of 20 is equal to d, right? So if I wanted to come up with the formula to compute d, it's just the square root of that, okay? However, when you have a d that is not 1, you actually want to change the values of x and y to reduce it to 1, okay? And that's what singular value decomposition is going to be doing for us. So whereas with our initial example, which is here, we can see that d is some big number. In fact, we maximize d, so it's probably some big number. The next step in our algorithm is we're going to try to shrink the model down by reducing all of these distances until I keep the same ratio or the same slope per se, but I make the distance 1. So you could think of like, instead of having this be here, I want to bring it down until this distance is exactly 1. So like maybe here. So what does this equal and what does this equal for that? Well, it's just simple algebra, right? So, and then the reason, why am I making it be equal to 1, by the way? Because that's called a unit vector, and that's going to come in useful for us. You can think of it like normalization in a way. Okay? So how do I take something that is currently d equal to square root of 20 or d squared is equal to 20 and make it into 1? Well, if I have this problem and I want d equal to 1, just divide both sides by whatever this is here. So divide both sides by square root of 20, and now you've got it equal to 1, right? And we know that with this formula, it means that I got to divide both sides by that. So let's go ahead and do that. So again, with the numbers that I have, with the 4 and the 2. So I'm going to divide both sides by square root of 20, and I'm going to get this. I'm going to get this, I'm going to get this one. And then and the next thing I want to do is I want to separate this so I can put it inside of the square root. So how do I do that? I square it, right? So I square it, so now I can put it inside of the big square root. Next thing is I want to split it so I can split this divisor into both of these additions. So I do it like that, okay? From there, I could also rewrite this like this if I plug in the actual numbers, the 4 and the 2. But what I really want to point out from here is that all I really have to do, like the shorthand of this is, all I have to do is I just have to divide whatever D currently is and take the X1 and the Y1 and divide them by that. So if all of this looks kind of, freaky, even though it's just basic algebra, shame on you. Really, all you gotta do, if you want to simplify this, so if you know in this case that D is currently equal to square root of 20, then just literally divide square root of 20 from Y and from X. And whatever that A is equal to is going to be your new X and your new Y, so that D is equal to 1. Okay, so that's the shortcut of this. But the proper math as to why that works is right here. So when we do that, when we do those divisions, we have a new X and a new Y. These are the new X and the new Ys. We have 0.89 and 0.44. I just plugged this in the calculator and went ahead and did it. What does this mean? Well, remember, to compute it, D, all we got to do is take X squared plus Y squared, and that's equal to D squared. So if I just take the square root of that, with Pythagorean Theorem, then I can compute D. So if I plug it in just to check to make sure that I didn't screw up, that's good checking your work, you can see that this is actually equal to 1. Also, I want you to point something out. The ratio between X and Y. So right now it's 4 to 2, right? So like basically a 2 to 1 ratio that we have here. That will also remain here. You can see that 0.89 and 0.44, that's about, but actually not about, it's actually twice, exactly twice the amount. So that ratio is still there, okay? And that's what I point out here. So before we had X4 and Y4, 2 to 1 ratio. Now we have these numbers, it's still 2 to 1 ratio, okay? The ratio will still be the same even though the values are different because the slope didn't change. You can think of the ratio as the actual slope, and the slope remains the same. All we did is we moved this, we slid the point down from being square root of 20 distance from the origin to being 1 distance from the origin. And then we updated the location of the point basically, which is the X and the Y. Okay? So again, PCI, principal component 1, sorry, PC1, is still telling us that X is twice as important as Y, right? In the other example here, where we had a slope of 1/4, then this is a 4 to 1 ratio, right? So in this case, suppose that we were looking at this point here. Suppose this was actually at like 4:1, okay? So if that was at 4:1, this will be 4, this will be 1. So what is D equal to? Well, Pythagorean Theorem. So 4 squared plus 1 squared is equal to 17. Right? So what is that? 16? Yeah, 17. Okay? And that's all equal to D, right? So if I want to do that same unit vector conversion, all I gotta do is I gotta take the 4 and the 1 and divide them by square root of 17. Again, if you don't see why this is possible to do like this with that simple thing, that's what the complicated math that we did, it's not complicated, but that's why we did this math. To show you that we can actually just do it like this. Okay? So if I compute that, let's see what that's equal to. For that, I'm not doing it by hand. 17. So this one is about 0.24. And the other one is 0.97. Okay, so I want you to take something into account here. So like notice something. Before we had that 4-to-1 ratio, right? And we actually still have that. Like, I mean, you know, it doesn't look right. It looks off by like a little bit, but like think about it. It's like if x was 1 and y was 25, then that would literally be the same, right? That would be 1 times 4. But like if we take 0.24 and multiply it times 4, we get 96. So where does the little 1 is left over? Well, that's because like this was actually 2425, basically. So now it adds up, right? It's got some decimals. But the point is the ratio is still there, okay? That's what I want to emphasize. So we're not changing the ratio or the slope. We're just changing the distance that that point is, okay? So maybe we'll leave this here. So why are we doing this again? Well, you'll see in a second. Okay, so we got the ratios. They're still the same, even though the values are different. And we still have the proportions. And by the way, these proportions have a name. And they're called loading scores. So the x and the y values that we just computed, those are called loading scores. So whenever you hear that, or whenever you're coding this in Python and you have a variable that's part of the Pca class or something that's called loading scores, that's what these are. That's what those numbers represent. So you can see those ratios. Okay? Also, important term here. Okay? What you just computed, the x and the y that are giving you that unit vector, that's called a singular vector. Okay? And it is also known as the eigenvector for PC1. Okay? So that might be a little bit of terminology that I just threw at you, but don't confuse eigenvalue and eigenvector. Eigenvalue is the sum of the square distances. Eigenvector, on the other hand, is going to be the x and the y, or how many dimensions you have. You could have 100 dimensions, then you would have 100 values, and they're all going to be less than 1, anywhere from 0 to 1, because think about the Pythagorean Theorem, right? What you're computing is something, something, and then this is 1. So therefore, both of these, because they're non-zero, they have to be less than. Well, actually, yes. If one of them was 0, then yes, it could be 1. Okay, so maybe I'll say 1 inclusive. So it can be from 0 to 1 inclusive of 0 and 1. Okay, but it's really rare because that means the line is going right to the point, which doesn't happen very often. But it can. So 0 to 1 inclusive. Okay, so again, 3-dimensional Pythagorean theorem is kind of trippy, or 20-dimensional, but the same rules apply. I was just thinking of trying to draw 3D Pythagorean, but let's not do that. It would be like a weird form of a pyramid. And yeah. But anyways, that's called eigenvector, okay? Those values that you have, all right? Also known as the singular vector. And therefore, principal component 1, okay? So we are like 80% done now. So don't fret if you're still, if you're like, oh gosh, it's a lot of stuff. So now that we computed the eigenvalues and the eigenvectors for principal component 1, and we know the slope because what's the slope? Just take one of the eigenvectors and that's your slope, right? So now that we've computed those values for PC1, we're going to move on to PC2. So how many PCs do we have to compute? Well, that's up to you really. Like, you could stop at 2 because each PC you can think about like a graph, but you can compute as many as the number of features that you have. And by the way, normally in our heads when we think of like using principal component analysis as a way to reduce number of features, let's say you have 10 samples with 3 features, then you could take those 3 features and make them into 2. But suppose that you had 10 samples and 30 features. In theory, you could run principal component analysis to reduce the number of samples but keep the same number of features. That's really weird. It's doable. Not something I'd recommend unless you know why you're doing it, okay? But it's possible to do, so I just thought I'd bring it up. But anyways, so we're gonna do PC2. PC2 is actually really easy to do. And all the other PCs are pretty easy once you get the first one. The first one's like the hard one. All you gotta do to find out the next principal component is just find the line that's perpendicular to your previous principal component. So that's pretty easy to do. Just find a 90-degree angle, right? There you go. Done. That's it. So what do you have to do now? You got to compute the loading scores, right? That's kind of easy to do too because all you did is have a perpendicular line. So given the loading scores for PC1, you can think of it like we have a little triangle again, Pythagorean Theorem. How would I find out what the loading scores would be for the perpendicular line to the hypotenuse of this triangle? Well, all you gotta do is flip the triangle. So like, you have it right here. And then bam, flip it 90 degrees this way. And now you have both hypotenuses being perpendicular right there. You see that? They're perpendicular. What you don't want to do is if you flipped it like, can I even do that? Like maybe, oh, yeah, like don't flip it like that. Or actually no, that's just weird. Don't mirror it. Yeah, don't mirror it. So like, can I mirror something here? Will it let me? I think you can, but here, let me try. There we go. Kind of ghetto mirrored, but like you don't want to mirror it because that's not a 90-degree angle, okay? It looks kind of like a 90-degree angle just because it's off scale, but it's not. If I actually make this look kind of like the previous triangle, which would be like this, that is not a that's like a 120-degree angle or something, okay? So don't do that. Just flip it from here like that, clockwise, 90 degrees clockwise, okay? So if you flip it, you all of a sudden have a perpendicular line, which is what you want. And so what is the location of what is the distance of the x and the y after you do that? Well, they should be the exact same, right? Because remember, the loading score right now, or the eigenvector, is already set up to have a distance of 1 for the hypotenuse, right? So when you flip it, that distance is still going to remain 1. So that means that your x and y are going to remain 1, although now they're going to change because you flipped it. So your y becomes the x and the x becomes the y, right? So as you can see, after I flip it here, the values are still the same. It's just that now the x one became y and the y became x, right? Because this was vertical before, now it's horizontal. This was horizontal, now it's vertical. So you just flip the location of them and then also make the bottom one negative because now the slope is going down, right? So before, the slope was positive. But now that the line is actually going down because this one goes up, or vice versa, by the way. If your fitting line was negative slope and then you flip it for PC2, it becomes positive, right? Because it's going up now instead of down. So just make sure you add that negative. So the quick trick is flip x and y and then make it negative. Or if it's positive, make it negative. If it's negative, make it positive. Basically multiply it times -1, which will get you the right answer regardless. Again, this is simple because it's two-dimensional graph. Harder to think about that when it's like three-dimensional, but it's the same concept of flipping it, okay? So these are our new loading scores for PC2, all right? This was me just really trying to emphasize the flipping, that in case you don't follow it. So I guess I'll re-emphasize it. So basically, you start with a slope like 2 over 4, which is the one that we have. And then now it's going to be -4 over 2. So, so I guess, yeah. So now to remember, I did this notes yesterday. Basically, I did an example where I got rid of the eigenvectors and went back to the normal values before we simplified it, the division by square root of 20. So the slope was this. Like this was the original slope of the line was 4 and 2. So now the line going down is -4, 2. So I guess it makes more sense when you look at the original numbers, and that's why I had that. Okay? Anyways, what does this tell us about this line, about PC2? Well, it tells us that y is twice as important as x for PC2. Okay? So it's important to know. It's important to analyze. PC1 is important, but PC2 is also important to know. Okay? So once you've done PC1 and PC2, and suppose that that's all you're doing, I mean, at most you want to do the number of PCs that you have features, but you're trying to do less, right? That's the whole idea of this. But whatever you decide, so in this case, just 2 of them, what do you do then? Okay, when it comes to graph it, you have to graph the new version, right? The new one, we're using the PC values. And so the way you graph that is you just take your values and you plug them in, you're good to go, right? But I want to show you a more visual way so you understand what is really happening to the data. Okay? So the first thing is, this is what the graph looks like now that we have PC1 and PC2 computed. So you can see this is PC1 and this is PC2. So what you want to do now is PC1, you want that to be your x-axis and PC2 to be your y-axis. Now, you could do it the other way, but I wouldn't do it. So you know, it's like, again, the same idea of like, I could flip x and y features if you want, you know, they're just arbitrarily picked. So yeah, I suppose you can. But it just things look nicer whenever PC1's on the x-axis. So yeah, so in this case, we're just gonna flip it or rotate it clockwise so that the PC1 and PC2 are actually horizontal and vertical. So that means that our actual x and y axis are now kind of flipped out, right? So when you do that, in this case, the points will actually also get rotated, right? So the whole graph gets rotated. So you can see the points actually got rotated. I can show you like a live version of the rotation happening. So like we go from here to that. That's all we're doing. From here to that. That's it. We're just rotating it. So the points get affected, okay? But this is easy to do because I'm literally doing it on paper, right? But when you're doing it on the computer, the easiest way to redraw the points after you rotate is just go ahead and look at the distances that make up the eigenvalues and then just replot the points that way. So in other words, look at where the collisions were. So like, for example, before we rotate, remember, what we computed with the eigenvalues was this point here, right? This distance, this maximized distance right here, that's the one that was part of the eigenvalue that you maximize and square these. That's D1, D2. And then PC2 also has a D1 and D2 technically. So just look at where that is, even though you kind of skipped doing that because you knew because you could just do the perpendicular line. You can go back and recompute that. So once you computed that, then you know where then you know where those are. So after you rotate them, you can remember where those are. So like, let's say this is like, I don't know, 2 here and 1 here. So after you rotate it, then you just go 2 here and 1 here, and then you have it there. So that's how you would regraph it if you can't just as easily rotate it. Okay? So that's the math behind regraphing it. And once you've regraphed it, what you come up with is your brand new and dimensionality reduced graph. So you're all set for the most part. Like, this is it. You obviously, you look at this and you look at the original one and you're like, they don't look that much different. Well, yeah, because we're going from 2D to 2D. But if we were going from 10D to 2D, this is when you would see the big advantage. And I'm going to show you that once we get to the Python stuff. So I wrote it here, because it's perpendicular, doesn't really change the position, but it would in the more complex, higher dimensionality example. Okay? Next, let's talk about computing variation. So variation is going to be what helps us to do some data analytics. Okay? So to compute variation, what we have to do is we have to take the eigenvalues and we have to divide them by the sample size minus 1. So to compute the variation, we're going to compute the variation for each principal component value. So PC1 and PC2. For PC1, what I'm going to do is I'm going to take its eigenvalue, that I know what it is because I've computed it already, and I'm going to divide it by the number of points I have. So say I have 6 points, and then subtract 1 from those, so 5, and then just do that division. Okay, so here's some random example. These numbers I just came up with. I try to come up with numbers that would make the math easy. So suppose that this is your eigenvalue. So we have 1. So the eigenvalue for this would be something like this. So the distances, like d1 would be 1, d2 would be -2, d3 would be 3, d4 would be 3, and d5 would be 4. So to compute the eigenvalue from this, what I have to do is square all these together and sum them, right? So that's what I have here. So I have 1 squared. Well, I guess I have -2 just to show you some negative numbers and show you how the square gets rid of that. And then have a couple of others. And then I have basically a sample size of 5. Ah, shoot. Oh, wait, no. I thought I screwed up the math, but I just remember I did subtract 1. But yeah. So if I do this math, I get 39. Okay? So that's my eigenvalue for this. 39 is my eigenvalue for PC1. And the sample size is 5 because I have 5 points. The word sample shouldn't misdirect you. It should be the number of points total for your entire data set that you're working with in graphing. Okay, so if you got 1,000 points and you got 10 features and you're trying to reduce it to 1 feature, or sorry, not 1, but like 2 features, 2 principal components, then it would be 1,000 for the sample size. Okay, which does mean that you would literally be doing 1,000 squares. So like you would take 1,000 numbers and square them and then add them together. That's a lot of work. And that's, by the way, every single time you're trying to compute the line and see how it fits. And then when you rotate it, you got to do it again. But eventually, you're going to come up with the best fitting line and a set of numbers that make up that, which is this. In this case, it was this value. Okay? So to compute the variation, I'm going to take that eigenvalue of 39. I'm going to divide it by 5 minus 1 because sample size minus 1. So 39 divided by 4. And my number I get is 9.75. This is known as the variation for principal component 1. I'm going to do the same thing for the other principal components, which in this case, all I have is just one more. So I'm going to take another one. All principal components should have the same sample size because it should. I mean, you're doing it on the same data. So there shouldn't be a scenario where like one component has more points than the other one, at least that I can think of. Well, yeah, it'd be weird. So anyways, we go and compute that. Again, I got some numbers in there. Again, I just came up with random numbers. I don't know if this actually would make sense, but it doesn't matter. I square them all, get that eigenvalue of 19, right? So eigenvalue of 19, so now I'm going to take it, sample size minus 1, so 19 divided by 4, and I get the variation for PC2 of 4.75. Okay, so what is my total variation? The total variation is just add up all the variations of all the principal components. In this case, I take 9.75 and 4.75, add them together, I get 14.5. That's known as a total variation of this, okay? So once I got the total variation, let's try to analyze how each of the principal components variation is kind of fitting into the big picture, okay? So just do percentages. So take the principal component 1's variation and then divide it over the total variation so you can see the fraction of the variation that belongs to principal component 1 versus principal component 2. So PC1 over the total variation is going to be 9.75 over 14, and it gives me about 2/3, right? So that fraction is about 2/3, 67%. On the other hand, PC2 is 4.75 divided by 14.5. That gives me about a third, right? 32.8%. So what does that mean? What does that mean that PC1 has 2/3 of the variation? Well, it means just that PC1 contributes 2/3 of the amount of variation. In English, so I have it here. This means that PC1 accounts for 67.2%, so 2/3 of the total variation around the principal components. This is important. Remember, one of the reasons that we're doing this was for the graph, right? We already finished that. We're happy with that. Now we're looking more about which features we want to keep for our model and things like that, and whether this principal component analysis and the graphs that came out of this is actually a good representation of the data itself. Because the graph might look pretty, but it might still not be a good representation. This is what it's going to tell us, right? The higher the variation, is particularly for an individual principal component, the better representation, right? If this was like 95% for principal component 1, it would tell us that whatever principal component 1 is made of is like really going to show us the big picture, even in like one dimension, because we only have one component. Obviously, if we have two of them, we can add both of those percentages together, which in this case would give us almost pretty much 100 because there's only two dimensions. But if we had 10 dimensions and we only added the first two, and that gave us like 95%, that would tell us that this 2D drawing of this 10-dimensional data is about 95%. I don't want to say 95% accurate, but it accounts for 95% of the variation, which is really good. That means that like we've done a really good job, and this 2D graph is like pretty darn good representation of 10-dimensional data. We can then look further, if we go back, at how PC1 is made up, that recipe of like the slope and everything, to see which features created that principal component. And then those are the ones we want to pick for the machine learning, because that's what it's made up. So you kind of backtrack to there, okay? So for now, let's just kind of take a look at what I just said. So this is what's known as a scree plot. It's just going to show us the number of variations for each of them. I didn't put the percentages here, but I can go ahead and do that. So like this is 67.2%, and this is 32.8%, right? And so yeah, this basically tells us how good each principal component is at telling us the data. And the more of them that we have, the more complete the picture. But of course, we don't really want to have more than 3, because that's already a 3D graph. Ideally 2. Like 3D graphs are cool. You can rotate them and see them. But like if you print one out and show it on a presentation and you don't rotate it, or someone's just not used to seeing like a 3D image, it doesn't tell them much. So you typically keep it with 2, right? So yeah, this is it. That's all there's to it. If you go for higher dimensions, like I said, your loading scores will have, for the eigenvector, will have more than just x and y. It'll have as many as the number of features that you have, and so on. But like when you're trying to compute the principal, the PC2, PC3, PC 20,000, it's just perpendicular. You might be like, well, what do I do after I find out the perpendicular? Well, think about it in like 3D. This is one way, perpendicular here, then the third perpendicular is like that way, right? So like one dimension, that's the PC1 that you compute using your hard math. Then you just have to do the perpendicular of that. Cool. Now if it's 3D, that's your third dimension. So you just find the perpendicular to the 2. So in 4 dimensions, even though you can't really draw a graph for that, there has to exist also that sort of cross that is perpendicular to all of them. So there will always be a perpendicular that you can pick. Okay? It's kind of hard to visualize, but you have to think into a higher dimension. Okay? So as I put in here, you can have as many PCs as you have variables or dimensions. You can also do samples if you happen to have less samples than number of features, which is kind of what I was talking about earlier, but don't worry too much about that. And so to conclude, for dimensionality reduction, do PCA, pick the top 2 principal components that have the highest variation. Like I said, assuming that they're high enough, it will be a good 2D representation of your high dimensional data. Here I just have a little brief example of like going from 10 dimensions to 3 dimensions, okay? So suppose that you do this graph. PC1 has like 40% of the variation, PC2 has 20, PC3 has 10%. That means that if you make a 3D graph with the first 3, you get about 70% of the variation. It's not amazing, but 70% is not too, it's okay, it's all right. Like I feel better if it was like 80. Definitely if you do something in 2D with 60, it's kind of weak, so I wouldn't be too happy about that. That's why I picked 3. But it's just to show you, right? Like you have to make that decision about that percentage of what is good and what is bad. If you do get something like this, which I hinted to earlier, that means that all the components kind of have the same weight. So that's kind of like a scenario where you just have to move on from principal component analysis to try something else, like discriminant analysis, UMAP, some other algorithm, because this isn't going to be a good 2D representation or even 3D representation of the data if you have all these principal components that are giving about the same variation. You can still use this to see even within the same, even within the components like which one's more important than the other one, you can kind of see, you might be able to get some useful information from that. You might also still be able to get some more useful information from the graph, and even though it's not as good representation, you could still see some clustering that you can then look further as to like, why are things clustering? So it's still all right, but you have to be careful, okay? Because you're not getting the full picture. So that's why I put it here. It can still be useful for detecting patterns, but, you know, little asterisk at the top of like, be careful. Don't get carried away assuming things based on that, okay? Now, something that I want to emphasize, it's a lot of stuff, so I hope I can find it. When we figured out PC1, we said the slope of that was like 4 to 1, right? Or like 1 to 4, I guess, 1/4. So that meant that like, or I guess in this 4 to 2, I'm saying that X is 2 times as important, right? So that feature is the one that we would want to keep for like a machine learning model, right? Notice something here. So I got my loading score and the eigenvector, right? So I got my eigenvector for PC1 and the loading scores and all that. And I can see that X is twice as important as Y. When I do PC2, technically Y is twice as important as X, right? So you might be like, wait a second, PC1's like said that X is more important, and now PC2 says that Y is more important. So which one is it? If that was a question you had earlier in the video, then that's very, very good on you. I'm proud of you detecting that. That means you're actually understanding what's happening. But the answer is also relatively easy to figure out. So yes, PC1 is saying like, yo, X is like the big shot. You want to make sure you keep that in your model as a feature. And then PC2 is like, nah, keep Y. That's the big one. Well, that's why we are computing the variation. Because when you do the variation, you can see that PC1 is 67 and PC2 is 32. And then remember, PC1 was preaching for X and PC2 was preaching for Y. So it's like, imagine you have two friends and you're taking a test, and both of your friends already took the test. And one of your friends says like, hey, you should really study principal component analysis. And that guy's called PC1. And then PC2 is like, no, study linear discriminant analysis, okay? And you're like, which one do you trust? Well, guess what? The variation is 67% for PC1. So like, you can think of like the credibility of friend PC1 is of 2/3 of the time he's right. And the credibility of friend PC2 is only 1/3 of the time. Who do you believe in? Well, you should go with the 2/3 one, right? Because he has higher credibility. So it's the same idea here. So yes, you may get contradicting results because of the idea that you're doing the perpendicular lines. So you are gonna get contradicting results. PC1 is usually gonna say like pick feature 1, and then don't pick feature 5. And then like you might get like PC2 saying pick feature 5, don't pick feature 1. That's all right. That's because you're going to use the variations to see who is right. And normally, like, you should get PC1 having the highest variation. Like, it should be, a graph that goes like this. So kind of what you see here. It should be like this. That's what you want. Because that's when you can say, like, okay, I should really believe PC1. Don't cheat on exams, I guess. Because don't ask your friends to tell you what people are telling you in exams, I guess. But yeah, you get the point. So like that's why you have to look at the variation before you just like immediately say like, if you get as far as computing PC1, you're like, oh, PC1 says to pick features 1 through 5 and ignore features 5 through 10, or 1 through 5 and 6 through 10, and then like you stop there. No. You gotta make sure the PC1 actually has a high amount of variation accounted for. Otherwise, it's useless. And that's why a scenario like this, where you have PC1 and PC2, this is like both friends have the same level of credibility and they're telling you opposite things. Who do you pick? that's when you should be like, okay, I don't pick either one. I go with my own thing. I do a different model, right? That's when you can't use this for selecting a feature that's better than other ones when you're doing reduction of features for a machine learning model. But you can still use it for graphing, picking at least two of these, so you have at least a little bit of variation, and then looking at that graph and detecting patterns, doing clustering and other things, okay? So there's always some use to PCA, but like it really depends on the data, whether that use is gonna be just looking at pretty graphs and trying to find new patterns with it, or actually giving you some really nice insight into like what features are important, which ones are not, and then getting some really strong graphs that really represent the data to like almost 100%. Variation, which you hope. Okay, so that's it. That is all I have on PCA, at least on paper. But now let's actually see PCA in action. So hopefully you retain some of this. Particularly, what you really want to retain is the last part I said, because that's when you actually understand what these loading scores and eigenvalues and eigenvectors, like you kind of understand what those are. So you can see whether you're, particularly with variation, if what PCA gives you is actually useful or not for reducing the number of features for a model, or for if your data is being represented correctly. Those things are important, right? Even if you don't really like remember like how the maximization happens of the line, or like you don't remember the square root of this, or the power of 2 of this and all that. Even if you don't remember that, you gotta know the basics so that you can understand this. Otherwise, like, it's just gonna, other than making pretty graphs, you're just gonna be kind of stuck. So, yeah, all right, let's do this. So, scikit-learn's documentation, as always, is really nice. So I'm gonna run you through 3 examples. I'm gonna run you through the Iris dataset with principal component analysis, and then I'm gonna run you to the Iris dataset again using a different graphing library, which I'm going to introduce you to, which I like, discovered, like it, pretty neat, pretty easy to use, because matplotlib and it can just be kind of nasty, especially with 3D graphs and trying to render them and all that. So I found this really cool library, so I'll show you that. And then the last thing we'll do is we'll try to throw this at the crypto dataset and see if, I know we said we were done with that data set, but I was like, hey, well, I have a data set, it's ready to go. Why not try to use principal component analysis on it? And then we just try it. So we'll do that as well. Okay, so we got a couple of examples, so let's get started. So with the principal component analysis, it's very easy to use in scikit-learn. All you really gotta do is import it like this. So you use sklearn import decomposition, and then decomposition contains a principal component analysis in it. In fact, it's decomposition.pca if you were importing just the PCA itself. Okay, so yeah, I'm just going to run you through this example. I went ahead and copied and pasted it from this page. So here we go. So we have Iris dataset from this URL. I'll leave it in the description below as well. And let's just kind of walk you through it. I didn't want to just code it from scratch because I think the video is long enough as it is. But you know, I wanted to run you through the code, and then I mean we'll code basically the crypto one from scratch. So in this case, let's just make sure that we understand what is happening. So they're importing NumPy, they're importing matplotlib. Don't worry about this for now. And then we got the decomposition, which includes the principal component analysis documentation. In fact, actually, I have this one too. Let me show you this one really fast. So this is the decomposition actual library linked to the documentation from scikit-learn. So you can see decomposition.pca, principal component analysis, linear. Oh, by the way, what I show you today is called principal component analysis using singular value decomposition. There's multiple principal component analysis. There's even regression principal component analysis and all this other things. Okay, so there's a lot more to learn. If you're interested in this stuff, if you think it'll help your projects, then I'm going to leave some links in the description to more tutorials on this and a lot of things to read and play with. Okay. As you can see, it says here, we're doing the dimensionality reduction to project it to a lower dimensional space, aka something 2D or 3D from like 20D. The input data is centered, which you know what that means now, but not scaled for each feature. What do I mean by scale? So a lot of the times, so principal component analysis is very sensitive to unscaled data. What that means is, like, think about like the crypto example, right? Some of the features there, like Bitcoin price, are like in like thousands, right? You know, 10, 20,000, 30,000 because Bitcoin's going up, right? However, other of the points, like for example, the Ethereum ones, or maybe like a percentage ones, are really small numbers, okay? So that can really mess up the components. It can really like bias them with big and small numbers. And this is not just a problem with principal component analysis, but in general with machine learning, this can be an issue. Like if you have features, because remember, all machine learning is at the end of the day is trying to come up with some formula for the slope of a line, right? Well, not all machine learning, but like most of the machine learning we've done, like regression-wise, all you're doing is coming up with the slope. And the line may be multidimensional with like 10 different x's for each weight, but at the end of the day, it's just a slope of a line, right? So computing that slope when each of the different weights you feed it in have a completely different range of numbers makes it very sensitive for, like, even if your slope varies by like 0.1, if the numbers you're dealing with are in like the millions, that's going to make a massive change, right? So it's problematic. And while yes, numbers are infinite, and I could also make a 0.10001 to 0.10002 change, it's not ideal. It has a hard time doing that. So one of the things you can do for that is known as normalization. And normalization is a really cool thing. It allows you to convert, or also known as standardization. It allows you to convert data that is from a range of, let's say, 0 to 100, and then you can make it into a more uniform. So maybe from 0 to 1. So you could take data that goes from 0 to 1 million and then shrink that range into a range of 0 to 1. And then data that goes from a range of 0 to 10, also shrink that to 0 to 1. And now they're on the same scale, so there's less of this issue. It's a very easy process to do. There is, of course, scikit-learn has a documentation and library functions for you to do that. They're called normalize. I was going to talk about this already, by the way. This just came out of nowhere. But I was going to talk about it later. But I might as well talk about it now since it kind of came up. And so normalization is, like I said, there's two ways to do it. You do it either with standard deviation or with the min-max function. And I think I talked about normalization in the support vector machine videos as is. So I won't say much more than that, but I am going to leave a link on the description to talk about how to use it. There's also a NumPy function you can use for that. And I'm going to leave a link to Stack Overflow with some people just doing some simple math. So yeah, we'll have plenty of normalization stuff to show. But that's the basic idea behind normalization. So that's why when you see things here about not scaled, it's saying that by default, the scikit-learn PCA does not do any normalization. It's up to you, which is a good thing. Trust me. Like, it's better for you to do that with and without to test how it affects it than for this to always do it and then someday you don't want to use it and then you're kind of forced to do it, right? So that's why they do it like that. Okay? But that's the reason why you usually normalize, not just for PCA, but a bunch of the stuff. And it's something that we haven't done with the crypto data set, by the way. But I think I might have done it in the support vector machine videos, I think. And if not, then there's tons of videos out there for normalization. And like I said, I'll leave link on the descriptions. But it's the basic idea of taking, like I said, a range of information that might be this big for one and this big for another one, and then combining them all so they're all on the same scale. So like, you can think of like one variable goes from 0 to like 1,000. Another variable goes from like -10 to -100,000. And maybe there's a variable that goes from like 5 to 10. And you want them all to be on the same scale of 0 to 1. And you can do that by just using, scaling it down. Like, you just basically change. And also, by the way, another thing, it's not a good thing to have zeros. Like, zeros are nasty for things like slopes and machine learning. So you have maybe you make it close to 0 as you want, but not 0. So that's another technique you tend to do to avoid like weird issues with your machine learning models. So for example, this data set becomes from like 0.01 all the way to like 1.0. So you shrink it to that, and then you do the same thing for this. This one you're gonna have to multiply to make positive. But you can see how I could minimize and maximize this to make this work like that. It's just multiplying it times a certain constant factor, right? So like, for example, this one's the easy one that I can do. All I'm going to do is I'm going to divide any numbers that I have in there by 5, right? So if I have a 10, actually, no, 5 wouldn't work because that would become a 2. So I'll just do divided by 10. How about that? So divide all the numbers by 10. So 10 becomes 1, and 5 divided by 10 becomes like 0.5, right? And so if we have a 5 in there, or sorry, we have a like a 7 in there, then it becomes whatever 7 divided by 5 is, right? So, and so on, right? So like you could do some simple math to do this, but there are proper formulas to do this. So like I said, if you want to know normalization, check it out. And if you don't, and you want me to make a video, you can let me know and I'll make a separate video as well. Okay, but I want to move on from that because that's not the point. Video is long enough as it is. Okay, so yeah, support vector machines. Sorry, so SVD, and I instantly went singular value decomposition. Okay, so you can see these are the parameters. The big one is the n components parameter. That is how many principal components you want to make. So again, you could make as many as you have features, but why? Better yet, you want to usually do 2 or 3 at most, because you know, if you're trying to graph it, 2D or 3D is as much as you want to go. By default, I believe it'll compute them all as well. The solver, you can play around with that. There's different ways of doing this, particularly fitting the line and other things. But now, when you see things like eigenvalues, you know what they're talking about. Unfortunately, we don't talk about the matrices, so you know that might throw you off. But at least you are halfway there with this stuff, as far as we can get to in this class for sure. And then there's some examples here of using it. Okay, but like I said, we're sticking to this example. Well, no, not that one. To this one. Okay, so this is the one. So the dataset importer is the iris dataset, which we have played with in the previous video when we were just looking at a logistic regression. And then so we are loading it in. We're taking the 4 features. So remember, these are the 4 features. The flowers, iris flowers. We got the sepal length, the sepal width, pedal length, and pedal width. And so we're trying to reduce it to 2 or 3. And yeah, so that's pretty much it. So over here, you're just making a figure. Don't worry about that. This is where you're doing the principal component analysis. So you use PCA, decomposition.pca. You put the number of components, like I said. In this case, we're going from 4 features to technically 3 because we're doing 3 components. You call fit, and then you call transform, and then bam, you're already done. And then the rest of this is basically just to graph it. So let me show you what that looks like. So the colors here are not coming from principal component analysis. Those are coming because we are feeding that in here as the labels. But what this is doing is, this is 4-dimensional data being shown in 3 dimensions. So you can definitely cluster it now. You can totally see how this is its own cluster. And then the other 2 clusters are really close, but you could do some machine learning to try to cluster it even on the principal components, I suppose. But yeah, so already here you can see how I've taken what otherwise would have been impossible to graph 4D data into 3D data. And this is still pretty complete in sense of like telling us that we have a robust model. Okay, so if you you know, don't want to show anything else in here. No, I'll show you more. Well, actually, here, why don't we look here. Not this one, but this one. So, you know, if you wanna find out some of the things like the loading scores or other things, you can see here that you can do something like explain variance ratio, singular values. So let's try culling a couple of these in here and kind of just see. So I'm gonna do it all the way at the end. So print Pca explain variance ratio. Let's do explain variance too, actually. I'm curious what that looks like. Okay, yeah, picture. We might need to comment this picture out so it doesn't like take a long time. What was the error I'm getting? Am I getting an error from this? Pca has no attribute explained variance. Oh, okay, so I guess this one's not getting it. That's fine. Here we go. So take a look at these. So these are giving us our principal components. So you can see that PC1 is accounting for pretty much most of the variance right there. You can see it's 92%. That means that this is a pretty good representation. In fact, if I just went with 2 of these components, which we'll do in the next example, that is accounting for like 97%. Yeah, 97% of the variation. Yeah, so like that's actually pretty good. So this is a good model. It's pretty accurate based on that. Just literally looking at like one dimension, it's already accurate. So like, oh, hold on. Rerun it, but like actually show the picture again. This is saying that this right here, this axis here, which is probably PC1, is accounting for most of the variation, which you can see is good because, yeah, like I can totally separate this and almost separate this. That's why it's not 100%, but I can almost separate this. Also, no, that's not why, because technically variance doesn't necessarily mean that the data is separable, linearly separable. It just means that this is still a good representation, as in like, no matter what angle I see it, it's still not separable. That's a better way of saying it. As you can see, this is kind of just like a mess all over the place, and then I guess those are the 3 dimensions, right? So we got this one with the vertical line. You can see that's like that, and then this is the 3rd dimension, okay? Which has the least amount of variance. So it's not really helpful for us. So yeah, there's your variance. Let's try, why didn't singular values work? Oh no, it's because I did explain variance, right? Let's try Pca singular dot singular values. Is that not here? Yeah, it is. Okay, why wasn't that completing? Singular values, prints the values to stream. Okay, sure. Yep, picture. Okay, so here you go. These must be my my SPAs. So let me compare them to what I have here. Oh, let me pop up my drawing. So remember eigenvalues. And now remember that the singular values are the square root of the eigenvalues. So what this is saying is, once I've found the best fitting line for the principal component, let's say PC1, that number is supposed to be the biggest it can be, right? So like the biggest number possible. And then I take the square root of that big number, and that's going to be my singular value. So now you know what those singular values are. So in this case, this 25 means that, what is 25 times 25 squared? 525 or 225? 25 times 25. I used to know a quick rule for that. 625, yeah. My bad. I just know that. Jeez. But yeah, 625. So that means that the eigenvalue for this is somewhere around a little bit more than 625 because there's some decimal values, right? For PC1, and then this is PC2, and this is PC3. I don't remember, but maybe there's a way we can actually print out the eigenvalue. The autocomplete is like not cooperating. I mean, I could just square those singular values to get the eigenvalues, but I'm curious if there's actually a parameter that score. What's that? Let's try that. Let's see what that gives us. Okay, we gotta comment out this graph because it takes a long time to run with it. Bound method score of PCA components. Okay, that was not good or useful. Noise variance. Okay, I'll leave that in there. See what that does. Okay, I'm not really sure what that is coming from. It's probably some computation, but I don't remember it. Feature names, get parameters, get position, components, feature, score. Did we already try score? I think we did. I don't see an eigenvalue, but I mean, we could just square the singular values and get the eigenvalues that way. Let's see. Scalar PCA eigenvalue. People are just saying to do math, which makes sense. That's fine. Either way, I guess technically speaking, you don't always get eigenvalues because it skips that. Because there's like matrix math that I didn't go over, which kind of says that you can't always get eigenvalues. But yeah, singular values is good enough. All right, just for all intents and purposes, remember that the square root of the eigenvalue is a singular value. So as long as you know the singular values, that's pretty good knowledge. Obviously, what you're looking for is that this one should be the biggest one. But more importantly, you want to look at the variance right here. This is the good stuff. This is what tells you if the PCI, sorry, I keep saying PC1, if the PC1 is good. You want this number to be as close as possible to 1, and you want it to have that arching going down like that. Okay? So, okay. I think we have run this example as far as we want it. So, again, I'm going to run it one more time just to show you what the graph looks like. And now I want to go and make it, since I saw that the PCA of this with the PC1 being so high, I can still do 2 dimensions and be pretty good. But I'm going to switch libraries. So now I'm going to bring the following. Where's that link at? Hold on. There we go. So I'm going to be using this plotpy library. Plotly library, not plotpy. Plotly library. It's open source. They have a paid version, but like you can use for free the open source one as much as you want. It's only if you want like support. It's kind of like, well, at least how Docker used to be. I think they changed now. But you can do some really pretty looking graphs with this stuff. So I encourage you to play with this on your own and like look at all of these. But this is also using the iris dataset. So let's try it out. Let's try out this one, 2D scatter plot. So here's the code. This code is coming from here. And let's just run it. Like I want to show you just like, look how many lines of code there are here. And yet like, just look at how beautiful this comes out. I guess this one you have to open up in a browser though. So that is the warning. So this is the same iris data set, but 2-dimensional, right? So using the first 2 principal components. You can see it's linearly separable. In fact, if I go back and run the other one, it's the same thing. It's just flipped this way. Right? Almost. This one looks a little bit, doesn't look, it looks almost the same, but not quite. However, you can see how even in this graph, you're really getting a sense of the three-dimensional data, which this in a sense gives you a sense of the four-dimensional data, which is the original one, right? So like, that shows you the power of principal component analysis. So first of all, this is 4D. So like you couldn't even graph this if you wanted to. But already with principal component analysis, I can do a 3D graph and it looks pretty darn good. But I can go even further because this data set allows me to, because of the high variations on the first principal component analysis, and on the first principal component and the second one together, giving me like 97% of the entire variation, which allows me to do a really good graph of this. So you can see how this graph really tells me all I need to know about this, which is like, this is its own cluster. This really should be its own cluster, and this. Again, the colors here are being given because we got the output, but even if we didn't have what the output is, or like what the labels are of this, you could very easily see that this should be its own species of plant, or its own cluster. These might be harder to cluster because they're kind of close together, but you could definitely see a difference here than here, okay? And if you want, if your goal was, if you didn't have labels and you were trying to make this into 3 groups or something, you could, like I said, there's other things you can do, discriminant analysis, UMAPs, etc., etc. But still, like from a visual perspective, this is good. This is really good. And again, data analytics, a lot of that, yes, you're analyzing data and like coming up with solutions and whatnot. But a big aspect of it is also to be able to produce good visual results for people that are experts and still like follow. Like you could try to convince somebody like, yo, I got this 10-dimensional data, but it tells me that like this stuff is its own class, it's its own group of like people or something. They're gonna look at you like you're crazy. But if you come back and provide them with either a 3D image like this or a 2D image like this, and you show them this, they're gonna be like, oh, you know, even somebody who's like zero knows nothing about machine learning, computer science, anything. They all probably went at least to high school. I hope, if they're your boss, right? But they can still see this graph and be like, you're right, this stuff is its own group. Like they could still agree with you on that. So that's the power of this. Now you could make a fake graph and show them, like, be like, yo, like forget about principal point analysis. Just make a fake graph where you just like plus a bunch of points and they look separate. Sure, you could do that, I guess, but you know that's kind of ethically wrong. Whereas this is actually a real graph with real math being applied that actually came up with this, and it can support your argument that indeed that this is its own cluster. Okay, so principal component analysis, great for dimensionality reduction for graphing, but also later on for you to then look further and do some machine learning on the specific features that are actually making up that high part of the recipe of the PC1 that you see here. Okay, because you saw that it's like 92% of the variation is just PC1, so you can see what the slope of that fitting line was and which of the features it tends to favor, which means those are the features that you want to take a closer look at if you're trying to reduce the amount of features you have because it's overwhelming or overfitting, etc., etc. Okay, so going back to the actual code, let's take a closer look. So this is the library. So how do you install this library? I actually installed it on this VM yesterday when I was testing this, and this is it. So pip install plotly. I just followed the documentation, which is found here, and they told me to install this version, so I was like, why not? And it worked. So feel free to install that version. Maybe install a newer version if you see this in the future. Whatever works. Took a few seconds, and yeah, success. Always look for this line at the end. It says success. Otherwise, look at the error and Google it, and get solutions for the error probably. Okay, so that's that, importing that. Again, I'm importing the PCA, except in this case, I'm importing just PCA. You could also do like I did before from sklearn import decomposition, but then you got to do decomposition.pca whenever you call PCA. Whereas if you import this way, then I can just do PCA like that. That's why it's done that way too. Oof. All right. So loaded the data set into a data frame, taking the 4 features that are in the data set, and then creating the PCA model. We're only going to do 2 components because we're going to make that 2D drawing where you already saw it. And then call the, you don't see fit being called here, but you see this one instead. That's fine. And then look, this is the cool part. Like, look, 1 line of code will draw you that graph. Compare that to like matplotlib, okay? That's why this library is pretty nice. 1 line of code, actually readable line of code, where you're passing in the components of what you got from the PCA. You're passing in the axis, and in this case, because you want it colored by the 3 groups, you pass that in. Bam, you do it. And that's how we got that graph. So yeah, this is pretty neat. We're going to use this library for the crypto one. So we'll actually code our own example there rather than matplotlib. Okay. And again, and this gives you like a little page. And this is actually like, you can zoom in, you can reset it easily. Like, this is so much better than like, imagine like remember the decision tree one, how painful that was? Or matplotlib can be iffy. This looks prettier. So yeah, I didn't get paid or anything to promote the library, but I am promoting it. So yeah, okay. Also, you can do a 3D one. So let's compare the 3D one. So this will give you the 3D one. So I went ahead and took this code and copied it in here. So this is the 3D one. Looks the same. Only difference being that I am using 3 components instead of 2, because I need 3 dimensions. And I am computing the variance because I want to see what the total variance is, just so I can show it on the top there. And it's 1 line of code, yes, still for the graph, but it starts to get a little bit complicated. But that's only because I'm putting in labels and I'm putting in a title. Other than that, otherwise, it would still be a very simple line of code to graph this. Okay, so let's run this one and see what it looks like, and compare it to the one that we had earlier, because it's the same data set, so we should get about the same results. So this one, you know, with 3D, I'll leave it up to your judgment to see if you like this one more than that one. I will say that I like the fact that it's easier to create the graph. Oh, damn, it closes it when I run it. Like, look at all the code, all this code to get this 3D graph going. And even I struggle with that code sometimes. But it does generate a relatively nice looking graph. And then this is the one for the other library. And as you can see, really, really high variance there. 99.48. That means that like PC4 is like half a percentage. So yeah, and you can see here the components, PC1. So if we do PC1 and PC2, that would be like this view, right? So that's what we basically did earlier, except it was probably flipped this way. Yeah. So that's PC2. And then PC3, which is the one that's kind of useless. You can see why it's just kind of like blah. I think I commented out so I could have both. Oh no, I don't. But I can throw it in. So well, I can just run this one. Yeah, let's just run this one. It'll open up in another tab. Yeah, here we go. So here's here's the graph with PC1 and PC2. And here is the graph with 3D. So you can see they're pretty much, let's put it in, I think we have to put it in like that. PC1 and PC2. So that's how this one came to be. See them? They look identical. Obviously one's 3D, but So as you can see, when you graph something with the first two components, it's the same thing as the 3D one, except you just add the third component as depth. But yeah, so that's how we came up with that. As you can see, the depth doesn't really tell us much information, because when would it tell us information was like if some of these points maybe were like here, or if like you can see how like things are very flat like this vertically. So that's why the third dimension PC3 doesn't tell us much in this data set. But yeah, this is a cool graph that very easy to make too. I think what makes the graph from the Plotly a little bit nicer looking here is because these are really thick dots. I'm sure you could modify the function call for this to make the dots smaller, and then this would look so much better. You know, I mean, it looks better if you zoom in too. But I think that's the only thing missing from this library right now. From default, it's just the dots are too thick. So yeah, we gotta find out a way. But yeah, I mean, if we take the code here that we had for the singular values and the variance, they should be about the same. So let's do the one for 3D. And then let's just comment out the graph. So because it has to load a browser each time, so it takes a while. So these values are pretty much the same that we saw earlier. 25 and about 92 and 3, so 97. So they're pretty much the same. In fact, if I go in here and I copy them and then I rerun this one, they're side by side, pretty much almost the same. 29.089 versus 29.099. The slight variation in them is because of the fitting line. So like, it's very difficult to, I mean, think about it. There's an infinite number of numbers out there, right? So like, the step that it does when it finds the right line, it's never going to be the perfect line, because it's like, you could technically go a smaller step, right? So instead of going click, 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 you can go like click, 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 click. But you could also go like click, 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 right? So that's why it doesn't always land in the exact same spot, because the beginning random guess, you know, could be slightly shifted, so those clicks make it land. But it's really close, so it shouldn't make that big of a difference. As you can see on the bigger picture, like, this is still about 92.4%. This is still about 5.3%. This is still, the singular value is still like 25. So yeah, all those things are the same, regardless of which one you run. And if I run it again, they would vary too. So yeah. And don't paste that. For the 2D one, if I run it, just close that. Oh wow, I got an error because I closed it before I finished rendering. Scary. You can see that we also get the same thing. So 25, 25, 6, and then 92 and 5. Okay? So, yep. All right. So now that you've seen our uses of it, I said, you know, for the last example, let's take our crypto data set and do some principal component analysis on that. And you know, I don't expect to get anything really useful out of it, but I wanted to show you my own example, because so far I've just kind of shown you the ones out there. But like, let's make one of us. Let's contribute to the world of examples with my example. So step one, let's take the linear regression Ethereum code that we've been using for a while. So, yep, let's just principal component analysis on the linear regression data set. I guess we don't need this line then. And let's just run it, make sure that it still works. So here we have a graph. It's a 3D graph. It's a poor representation of the data because it's just showing 2 of the features that we're using, and well, no, 3 of the features, I guess. But you know, there's more features than that. In fact, this data set that we have has a lot of other features we never even used. And yeah, we can improve this now that we know how to with principal component analysis. So let's go ahead and do that. So I'm gonna go ahead and I'm gonna leave all the loading in that we have. And really the big work I'm going to do, I'm not even gonna run the machine learning stuff. Yeah, okay, so I'm gonna just do all my work here. So I'm gonna call this like the start of new code for Pca. Okay, so that's going to be all the new code here. And I'm going to call exit just so that it, like, you know, when I run it, it doesn't have to do the machine learning every single time. So yeah, all I have right now is a nicely loaded data set into this BTC ETH DF or data frame. And let's just try to do principal component analysis on the features and kind of explore them, see how they relate. Obviously, it's kind of weird. Like, I don't know what to expect from this, but that's the whole point. That's why I'm doing Pca. I don't know what to expect. Maybe I'll find something thanks to this. Maybe I won't, but at least it'll look pretty. So yeah, it's a good starting point. So even if you don't know what you're looking at, that's kind of the whole idea behind like unsupervised machine learning, right? You're just exploring data. So let's explore the data. Let's see what we learn from it. So first thing is I'm going to bring in my Pca, right? So from sklearn decomposition, import Pca, right? So import principal component analysis. All right, so I got Pca in here, and now I want to feed it in the data frame I have. Now, if I feed it in as I have it right now, I'm going to get an error because Pca expects numerical values. So let's go ahead, and I know I dropped already one of the date columns, but let's just drop the other one. Now, if I really wanted to keep date, I just have to turn the date into like numbers, like day 1, day 2 is like 1, 2, 3. Too much effort right now, so let's just literally just drop the date and you know, keep everything else. So drop non-numerical column. Now we should normalize the data, but yeah, we could normalize the data. We'll come back. I want maybe we show like before and after normalization. Okay, so like, you know, important really wishes normalize data first. Yeah, but I won't for now. Maybe we'll do that at the end. Okay, and then we can see how it makes a difference or not. Like, we'll see how it changes like the variation and things like that. Okay, so yeah. All right, so let's go ahead and actually do the Pca. I'm excited. I hope that like this actually does something cool. Maybe it will, maybe it won't. Okay, so let's do Pca. All right, so let's start by making let's make just Pca with all the components so that I can see like what comes out of this. Okay, so for now keep all principal components because I want to see what like the variations come out of this and whatnot. Okay, so let's use the same line that they did in the other library. So we're gonna get components, fit, transform, and then we're gonna feed it in the data frame. Okay, and that's it. We have just done principal component analysis. So now let's actually, here, save some time. Let's just copy paste the variations. I want to see what we get for that. Okay, let's just run it. I'm excited. Wow, it's a lot of numbers. Which is which? I guess this one's that one, and this one's that one. So, oh, there's some nasty numbers here. I don't like how complicated they look. Okay, so let's comment them out. Just to compare, so remember, when we run this over here, not surprised at the same time. It's probably because of the lack of normalization, and also the fact that the data is like, it's a time series, very weird. But you can see like this is what we wanted. Like this is kind of what we're looking for, right? So like when we do this, you know, the variance. Let me where is it? Over here. So I'll keep this here for reference. So like this is what we're looking for. So like we want a high variance in the first component, or at least like the first 2 or 3. And then it doesn't really matter what we get for these, but you know, we do want to see the number here being bigger than the other ones. So when I'm running it for this, well, let's start by looking at the variance. So this number is definitely bigger than the other ones. Remember, the scientific notation means that when it says something like 10 E01, that means 10 to the, that means basically 10 to the okay, let me just do this in the iPad, easier. So when you see something that says like 9.73 and then a bunch of numbers and that says E01, what that means is 9.73 times scientific notation, 10 to the negative first power, which is the same thing as 0.973. So if you saw something like 8. Okay, I'll just do another one from here. 4.52 E09, that's the same thing as saying 4.52 times 10 to the negative 9 power, which means you have to put basically a bunch of zeros here, 9 of them, right? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 4, 6, 8, and 9. I say 9 because I include the one before the dot. But yeah, so that this would actually be that number, okay? So really tiny number. So the bigger the power here with the negative, the smaller. Now it goes both ways. So if you saw something like 5.11 times 10 to the 5th power, what that would be in the Python talk is 5.11 E05. Okay, so it would look something like that. Make sure you keep an eye if there's a negative there or not, because that means it's a really big number or a really tiny number. Okay. So now that we kind of refresh scientific notation, we can see that the variance of the first variable is literally like 0.9. That's really bad. That's basically telling us, I mean, sure, it's bigger because like you can see how the exponents become bigger here, negative exponents. So like this is like 14 zeros, like 0.00000, and then there's like a 6. So it's a really, really tiny number, and this is really big. So at least, you know, within this craziness, we're basically saying that it accounts for the first component accounts for at least almost 1% of the or actually wait, not 1%, actually technically no, this accounts for 9% of the variance, right? 9 or 90%. Oh no, wait, is that 90%? Really? Why is it using scientific notation for such a small number? 0.9. So so this is 97% of the variance. So actually, this is really good. Really? Like, my mind is blown right now. Why did it show with the scientific notation for that? But yeah, because I mean, compare like 0.92. That was 92% of the variance. What we're getting right now is the equivalent of like 0.973, right? That's basically this. That's like amazingly high. And then the second one is 0.026, right? 65. Because we got 1, 2. So yeah, so I just went from like shake my head, principal component failed on the crypto data to like it actually worked pretty well on the crypto data. Or at least it seems that way. But then again, it's not normalized. So there's probably some weird, finicky nastiness going on. So, you know, I will kind of, you know, I will look at this suspiciously until we're finished with this example. But it definitely has. I will watch this with great interest. Watch your career with great interest. Okay, so yeah, very cool. All right, so far so good. All right, let's look at the singular values. Those really won't make much sense because they're just, you know, like the square root of the eigenvalues. So it's like some math that happened. I mean, yeah, like as you can see, there's some numbers. This is a really big number. It's a massive number. Like, holy smokes, that's like what is it, like 3 million almost? Basically, I gotta move the decimal 8 digits. So 3, 4, 5, 6, 7, 8. So 340,618,254. So that's a big number. Think about how hard it was to compute that. So for the computer, and yet it did it fast. So yeah, some big numbers. It does seem that as you get smaller with the components, the numbers become small. That's okay. Yep, not bad. Remember, we're trying to maximize those numbers. So the bigger they are, I guess it's hard to compare them because you have nothing to compare them against. Like if you had a wrong line to compare them with, then yes, these numbers would be bigger than the ones, right? Because like when we did this, you know, and I compared you like. Oh God, there's so much writing when you think about. See, aren't you glad I wrote this ahead of time? Somewhere in here I have a little tiny graph. Oh, I missed it already. Hold on, let's just go all the way to the top. This one. So remember, the bad fitting line there gave us basically a 2, right? Give us a 2 for the eigenvalue, which means that the square root of 2 would have been the singular value. When we had the right fitting line, we had a 10. The square root of 10 would have been the singular value. So which number is bigger? Square root of 10 is bigger. It's going to be something like 3.2 or whatever. Whereas that one's like 1.4 for the square root of 2. So obviously, bigger number is better. Hard to compare because we don't have anything to compare it with, but just kind of like know that this is the biggest that it could have achieved within the error margin. So, yep, okay. So anyways, in conclusion, this is going pretty well. Like, I mean, at least based on the variance ratio, I am surprised that this is doing good. Let's print out components. I'd like to see those. Okay, so we got our components right there. That's the actual data that we're going to be graphing. So yeah, looks fine. Okay, so let's graph it. We're going to go back and normalize it. I'm actually curious to see now how normalizing changes those values. So let's actually save them. particularly these ones. But I'll save a little bit of that one too. So I'll put them in a notepad. So I have that saved for later, so we can compare them with the normalized ones. But yeah, let's go ahead and graph them. So to graph, we are going to do the, here, let's just copy paste again. So let's just copy paste the import plot pi, plot li, dot express as px. And then we can do both the 2D example and the 3D example. Let's start with the 2D example, since I showed you that one first. Plus, that one was the one that looks nicer on this library, in my opinion. Again, this is going to be super easy to do. All I have to do is call this px scatter plot, and then just pass in the components, which is the name of the variable. And then I don't really have to pass any other parameters because like I don't have a color for the classes or anything, so I'm just gonna pass those two just so it has something in there. But I could label them, like, you know, you could see here, like I could pass this here, like if I wanted to make it fancy. Title crypto data, and then total var, how is that computed? Copy this one here. So I could get like the total variance, which is basically this guy here. So the one we already printed. I'm gonna, oh yeah, this is good. It'll give me the total variance as a sum of those two. Although, no, this is gonna give me the sum of all of them. Okay, so actually, let's change this to have only two components for now, okay? So PCA and components 2. So keep only 2, because we're gonna make a 2D graph, so there's no need for the other ones. And that way, actually, we can see it all. So before I run anything else, let's call exit. I don't want to spoil this. Okay, so now it only has the first two. Oh, look, it looked prettier now already. That's nice. I didn't like how the other ones looked. But yeah, you can see that like most of the variance is coming from like the first principal component. It's amazing. Like it's 97%. It's even better than the iris data set. Like, oh my God. This feels good. But yeah, so, okay. So yeah, we're gonna have it print out the total variance as a title, and then the labels, yeah, we'll have it labeled like that. Actually, we're gonna do 2, so let's get rid of this last label because we only have 2 dimensions. And yeah, like I said, we don't need that. I could have literally left it like this, but might as well make it look pretty since now it looks like we're gonna have something nice to show. So yeah, okay, let's show it. Big show. All right, and let's see it. I hope it looks pretty now. I'm all hyped up now to see like an amazing looking graph. And I mean, yeah, I'm pretty happy with this. This looks nice. Like you can clearly see the most pattern of the data is here. You can see this is a cluster right here. I would be interested in finding out what this is. I would also be interested in finding out what these are. And then I can study the outliers on its own. I can definitely study the main cluster here, which you can see this is like the main cluster. This appears to be its own cluster. So like already there, I have so many things that I could work on this data to explore. I could explore what this is. I could explore what this is, the main cluster, of course, and then look at some of the outliers. But definitely like this tells me that these outliers are totally different than these outliers. I wouldn't even call these outliers because they seem to be running on the same pattern right here. You see that? You see this little arch right here that includes these 2 points? That's super cool. Like, look at that. It's coming arching and then it goes here. And then these are coming here. So I could actually say this is one cluster, the one right here, it's almost like a line. And then this one that starts here and takes these two is another cluster. And then I got this cluster here, this cluster and this cluster, which could actually be related. And then I have the outliers, which I don't know where they're coming from. This could be a cluster too. Like this could be the outliers of this cluster. and then these could be the outliers of this little cluster. Like there's so much to look at this data to try to understand it. And I mean, of course, I don't know, like if any of those clusters will be relevant. This might, but like that's what I can look at. And if you find some relevancy, and then you want to show your boss, then you could tell him exactly what I said. Like this looked like random data, but it's not. It's actually part of this. And you can see that this is 100, but it's not 100. It's probably like 99.9. In fact, it's, I'll tell you, it rounded up because of the 2 decimals, but it's 99.9. Wow, it's like 999, definitely 999, but it's not 100, okay? So it's definitely not 100, but just those 2 features tell us at 100. So like now I could start to look and see like, why is PC1 such a high variance? Like which of those variables of the features are having that high slope or that low slope, like defining the slope of the line of the component. I can study that, and then I can use that in my machine learning or in just in general analytics to say like to find correlation between different features. Okay, so like patterns, like okay, the price is really affected by this one thing, and then you can find out. So pretty cool, pretty cool. I am very, very satisfied with that, like very satisfied. However, I still want to try it normalized, but I'm going to leave it like that. Let's try to do a 3D one now. So for the 3D one, I am going to rerun the PCA. I'm going to have to like awesome because it is awesome. Okay. So for 3D, I'm going to do PCA 3D, and then that's it. I mean, I'm just gonna, I don't need to recompute, but I guess I will recompute that. Recompute the variance, which is still gonna be 100 now. It's gonna be closer to 100. It's gonna be like 99.99999. But yeah, I'll compute that again. And then, I'm gonna need the third label. So it's gonna be 3 PC3. Okay, and fix show. Actually, I'll leave them both for now. It'll just take a little longer to run. Oh, wait. Yeah, I was gonna say I forgot to actually run it. I forgot to do the transform. So very important line right here, which is to actually run the PCA. Okay, so that's our 2D one. And something went wrong. Hold on. Let's do Fig 2 or something. Fig 2 show. Fig 2 show. That sounds interesting. Let's try that again. Oh, hold on. You run it differently. The line, this line should be a little bit different. You can see it here where I have the 3D one. It's a scattered 3D plot. That's the difference I have to do. So my bad. This Fig 2 is scattered 3D. I think it's scatter 3D like this. How was it? Yeah, 3D. So yeah, sorry for that. Okay, so here's the first one, and the other one didn't work. And now it died. Okay, hold on. What is up with this? Px scatter 3D components. Oh, I need the z variable here. Is that why? Is that really why it was like not working? Okay, fine. It's like, come on, don't let me down this time. There we go. So I guess, yeah, I was yelling at her for that. So that looks weird and trippy, to be honest. This one's looking at PC1 and PC2. So let's see how that looks before. So I think, oh, that's weird. PC1 and PC2. So I think for me to get it looking the same, yeah, this way. So this is the same perspective as this one. Interesting, because like, you see this? Okay, so this all looks now like this. Obviously, again, I don't like the thickness of the dots, but interesting, because like you don't really see like you don't see that big thing that we just saw, which is like that, like ooh. So even though this is very little of the variance, like less than 1%, less than 0.01%, it's still viable. Like there's still a merit to be said of graphing the 3D version of this, because like I would otherwise not have noticed that. And then I can look at that further. I can also see, look at that, see that versus this. So that's interesting. However, I would be careful to not get sidetracked with this stuff, because remember, these are just the principal components, not the actual features. So really, I should stick to this one, because this is most of the variance. This is just some noise. So worth seeing and worth maybe looking into later. I would still first focus on the first two components and what the features are that are defining that. Particularly not even the second component, the first component. Like this could be a one-dimensional graph, which I never tried to do with this library, but that would also be worthy of looking at as well, because like PC1 has like, what was it, like 97, 99%? It's really high, like ridiculously high. Yeah, 97% of the variation. So like that is the one that I want to look at closely and see how the features were decided, like what the weights of those are. Okay, but yeah, this looks pretty neat. Although I'm really happy with the results, I do want to do the normalization to see how it changes it. Maybe like our life, maybe they will screw everything up and it'll be sad and tragic. But yeah, I guess we can always undo it afterwards. So yeah, let's normalize. How are we going to normalize it? Well, we can try both the standardization and the min-max method. So let's use that sklearn preprocessing. Okay, to make our lives easy. I think that will be good. Well, we could, but I don't really need it. Because I have a data frame. I'm just gonna go directly and do some math. Yeah, I'll do some math. So we're gonna have normalized x, and then that was gonna be, I guess, standardized, and then min-max. I'm a fan of min-max versus standard deviation normalization. For machine learning purposes, standard deviation is just weird. Like, you can read my dissertation. I have a section dedicated on normalization, and I basically say anything I could say right now about why I prefer it for machine learning. But that's like not something that I discovered or anything. It's pretty commonly known. Standardization, using standard deviation to normalize, doesn't get you that many good results for machine learning stuff. For math and other places like statistics, yes. But for machine learning, min-max is the way. So this is the way. Okay, so yeah. So to normalize, if you wanted to do like the normal standard deviation, what you do is you take the average of the data, so you mean for that, and then you divide that by the well, so you take each item and you subtract the average from each of them, and then you divide the standard deviation from that for each point, and then save the results of each point. So for each point, take current point's value. Actually, before you do anything, find out what the average of the data is. So that's what this gets you. After that, find out what the standard deviation is of the data. Okay? Once you find those two values of the average and standard deviation, now you're going to standardize the data by going through each point and taking the current value of the point, subtracting the average, and then dividing it by the standard deviation, and then save the results of that. Do that for every single point, which this is what this is doing in like a really compressed code. Okay? So that is the standard deviation or standardization of your data. Standardization using standard deviation. Okay? Which not so good for machine learning. And then for min-max, what you're going to find out, and this is actually the real formula that we could have used earlier for that example, is you find out what the minimum of the data is, so like the smallest number, and then you also need to find out what the largest number is, which you can do by max. Okay, so once you find out both of those numbers, what you want to do is you want to find out what the range of them is. So find the biggest number and find the smallest number, subtract them, and that gives you the range of the data. So like if you have 10 and 5, like we did in that example, you take 10 and then you take 5 and then you subtract. So 10 minus 5 is 5. So I don't like that example because it's like, okay, let's do 10 and 4. So you take 10 and 4, so you take 10 minus 4 and then you get 6. So that's your range. That means you have a range of 6. So you're going to divide by that. So now for each point in your data, so let's say you have an 8 in your data, you take the minimum, which is 4. So you do 8 minus 4, gives you 4. Okay? Divide that by the range, which is 6. And then 8 minus, I said 8, right? So 8 minus 4 is 4. Divided by 6, that's 2/3, right? So that's 0.66. So that's your min-max method. Min-max will give you a range between 0 and 1. Okay? So yeah, so another example. Let's say that you have a 7. And your minimum is 4 and your maximum is 10. Okay? 7 minus your minimum, which is 4, is 3. And then take that 3 and then divide it by whatever the range is, which we said is from 10 to 4. So 10 minus 4 is 6, right? So take that 3, divided by 6, it gives you half. That gives you 0.5. So that's what you do. Okay, and yeah, let's do an exit so we can see it. And then let's just print these out so you can see them normalized. Like I said, there's tons of videos and stuff online, so I guess if you really want, I could do a video, but I don't think I need to do a video on that. I just kind of went over it right there. Oh, I guess these are the normalized values. Okay, so here is what I think. Okay, so these are the standard deviation values. You can see the range is more than just 0 to 1. You can see right there. And then you have your min-max values, which, ooh, what? Oh, did I flip those somehow? Why am I getting, those values do not look right. They look all weird and messed up. Or at least they look flipped. Here, hold on, let's comment out. Let's make sure that that worked. These should all be between 0 and 1, but I think this got screwed up somehow. Maybe it didn't do column wise, it did like row wise and screwed it up. It's ironic. The standard deviation ones look better, but I don't trust that any of that went down correctly. I don't know what happened with those. But hey, I'm curious, like, let's let them be. Let's see, let's actually see what happens with it. I know the data's all messed up, but like, even though we have some weird messed up data, I'm curious what happens if I try to repeat it, that data. So let's just try feeding it like the normalized one, because that's the one that looks somewhat better-ish. So what happens if I do? Oh, wait, I forgot to hit the exit button. Let's see what happens. Normalized x is not defined. Normalized b. Oh, the data got all weird. Not surprised, because who knows what we did to the data. But it looks cool. Oh, I moved this by accident. I hate it when I move this because it decenters it. Where's my browser? Oh, I gotta run it again. I can see the browser pop up. There we go. So yeah, I mean, like, data looks cool. We got a cluster here, and then we got like another cluster there. But this is all invalid data probably, because I don't know what happened with the standardization or normalization. But still cool. Still cool. Still definitely whatever we did, there's some pattern that we can figure out. Now why didn't that work? I guess we gotta go row by row. Okay, so maybe I really wish that just worked. So probably what is happening is this is taking the mean of, oh yeah, this is taking the mean of everything. So it's, you should be normalizing every single column on its own. So each feature should be normalized within itself. I think this normalized like everything together. So, but even if it did that, then we should still never get any number bigger than like -1 to 1 if we have negative numbers. But yeah, so I mean, I guess I could do like a for loop for I, and so this should give me the keys, if I recall. Let's just try that out. Yep, so these are all the keys that I have in here. So for each of the keys, what I want to do is I want to normalize those. So, all right, maybe this will work. No guarantees. Let's just do min-max. Because min-max, I know what the answer should be. It should be 0 to 1. So let's make I. So let's make, for example, this is going to be like for BTC high. I want to normalize the BTC high category. So I think if I do it like this, I think I'll be okay. Can I do that in 2 lines, please, Python? Don't yell at me for not being the same lines. Did it work? Syntax errors. Oh, yell at me. Okay, whatever. We'll let it be in 1 line. It's really thick line, but whatever. Let's see if that got actually normalized. So print. So here, let's remove this for now. And then comment all this out. And then just print BTC ETF. Let's see if that actually normalized it. My dog is angry at something. We got the same result. Why? I don't know. I don't know why. Like, maybe the parentheses are messed up somewhere. Maybe. Hold on. This could be something so much simpler than it might be. So let's see. So, for example, if I have somewhere in here like min-max. So this is like the formula for this. Here, I just found this on Google. I'll post a link to it. So we take the value, we subtract the minimum, and then we divide it by the range of them, max minus min. Maybe because there's like, is there negative data that's screwing it? But yeah, So take the value of that spot and then subtract it from the minimum of that. Yes. Take that, divide it by, and then take the max. Oh, haha, yeah. So that parenthesis was missing. Oh God, was this all because of a single parenthesis? That's so. You know, I think we've all been here before, so there's nothing more to be said. So okay. Let's see if it would work this way though, with a single line here. Let's see if that would have worked. Yeah, that would have worked too. Yep. I don't know. We'll look at that later. So, all right. So we don't need any of that. But that's, I mean, you can see how you do member-wise if you needed that ever. But yeah, so we don't need any of this stuff. So that means that the standardization one's probably okay though. That one was just weird numbers, but I guess they were okay weird numbers maybe. So yeah, let's backtrack a minute here. So we got normalize. Let's make sure that is all okay. So this minus the mean, yes, divided by the standard deviation, and let's just make sure that standardization formula. Yep, yeah, that's okay. So that one doesn't need anything else. It's correct. And in fact, I'm actually going to call it standardize. Standardize. Okay. And then this one now is fixed because I put the parentheses. All right, so let's run this. So yeah, normalization looks okay now because you can see the numbers are between 0 and 1. That's how you know that everything's okay. And then the standard deviation ones, they give me whatever. But yeah, okay. So everything is good now. I don't know why it's giving me an error. Was not closed. I don't know what you mean by not closed. Yeah, ignore that. But yeah, okay. So now we can test the normalization by saying assigning it whichever one we want. So first, let's do the standardize. Why am I getting an error there? It's still running. I don't know. That's just probably the VS Code, like not parsing stuff. Okay, so this was actually legit. So this was a legit result of the standardization. Okay, so that's interesting. Like, we have these two clusters. You know, we would definitely want to take a look at that closer. This is just a mess though with the 3-1. Like, I can't understand this at all and get anything useful out of it. But I suppose that would be PC1, PC2 like this. Would look like, I think this is the right version of that. Yeah, like that. So yeah, you can definitely see there's a cluster there and a cluster there. But now the min-max, which is the one that I'm actually really interested to see. I apologize if the video has gone too long because of the typo with the min-max. I shall walk the walk of shame later and cry. But hey, that's what happens with live stuff. Oh, wow, that looks cool. That looks pretty cool. I mean, I have no idea what it means, but it looks cool. Looks alien technology right here. So this is normalized. So I am going to give it certain validity because, like I said, normalization is actually a big deal. But before I even look at the pretty pictures, what are the variances? Like, what is the singular values? I actually need to know that. Where do I print those out? It should be at the bottom here. So my singular values went down. Before we had 97%, now we got 87% and 5%. So like a total of those together, you can see it's 92%, right? You see it here. And if we do 3, then we get up to 95. But I like these. I like the 92% with the 2. So I am gonna actually give this more weight than the not normalized version, because normalization, like I said, is a big deal with principal component analysis, and you should be doing it. So even though the other one was cool and I still want to look at it, this one I would look at before the other one. Okay, so I can see, I mean, these, you know, again, whatever, these, you don't really know much about them because they're just these are just, I think I said earlier wrong. These are just the singular values, but then this is the actual variation, PCI variation, PC1 and PC2 variation. So that's like whatever, it's fine. But now, the graph. That's interesting. So this is a representation of the graph. Definitely you can see that this is some sort of cluster, and then this is another cluster, and then there's some ambiguity here. And like you can see, like, you know, here's what I'm thinking. Knowing that this is the crypto data, this is when the price was lower, you can see the increase, and then this is when the price was bigger, also the increase. And similarly here and here. That's what I'm getting a sense of this. So this is like, you know, like before, like the 4-year range, or how many years we have for this, and this is like some part of the years, and there's another one. This is definitely a cluster, and this is a cluster, but this cluster and this cluster are related. You can just see it, like feel it, but you have to run other stuff to see. So this is really cool, and this will definitely make something of a cool presentation. Again, this, I gotta figure out a way to increase the thickness of the dots. Leave it in the comment below if you figure that out. I will probably Google it later. But until then, the 3D one is not that useful. It's still pretty to look at though. But this is cool. So yeah, I think this is the record for the longest video, so I should stop now for sure. So yeah. I mean, or maybe we should just go for the 3-hour mark, just so we can say we made it 3 hours long. We could do that too. But you know, it's a big topic, principal component analysis, and I really wanted to just not just go straight in and just like be like, hey, this is how you do it, kind of like how we did random forest. We're like, hey, there you go, and like I might have said decision trees, how they're made, and we spent like 5 minutes on it, but let's be honest. We don't know the technical stuff behind decision trees enough at this point. And that's okay. You can still use them. With principal component analysis, I think without knowing the technical background, it's not useful at all. Like, you run principal component analysis and you get this graph and you're like, okay, there's a high percentage number here, so I guess it's a good drawing, but like, how did it come up with it? So like that's it. That's where your knowledge ends, right? But now you know. Now you know, because you can look at the variation of each component, and you can be like, okay, the first component accounts for 87% of the variation. That means that component is actually, this graph between the first and second component are pretty much going all the way to 92%. That means that this is a good representation of higher dimensional data in 2 dimensions. How high are we doing, by the way? Let's see. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're 12 dimensional data. We are compressing it to 2 dimensions and doing a pretty good job. And 3 dimensions, even better job, 95%. So I think we're doing a pretty darn good job at visualizing very high dimensional data in 2 dimensions. So that's the first win. The second win here is that now that I know that the first principal component accounts for the majority of the variation, I can go in and I can see what the slope of the line is per se in that higher dimension, which will have different variables. And I can see which of those variables or features are the ones that have the biggest weight that generated this principal component. and then I can pick those as features that are actually, that define what the data is doing. You know, that actually inform us, that are independent of each other enough to actually have, like, to give us good information. And the other ones are just correlated or just like useless. They're noise. And so if I'm doing machine learning, I can focus on those features specifically versus throwing in all features at once. And I can study them further to see what the connections are. In this case, like with the crypto, you know, if I find out that the feature that weighs the most is I don't know, the percentage of the volume, you know, then I might be like, oh wow, okay, the price changes have to do a lot with volume. Maybe that's because there's a lot of panic buying or panic selling. So I guess that makes sense that volume is such a high valued feature in that first component. That actually makes sense, by the way. So if that was the case. So yeah, it's really cool. So, you know, study this stuff. Try it out on your project, see if it helps you, just like any other model. I mean, this is a little different. You're not doing, like, you're not predicting stuff right now. You're just analyzing stuff. But then again, I think if anything, this stuff is more like data analytics than like machine learning. So yeah, I think it's worth it that we spent all this time on this, because it's useful. And there are other things like this, like other machine learning, other algorithms and models that you can try out that do this kind of stuff. And I will try at some point to make some videos in the future of that. No guarantees that they'll come soon. Not for this series, but I do want to explore discriminant analysis and UMAPs at some point, because they're pretty cool too. But at least I wanted to get you one of these types. Okay, so we got this in there, and I'm pretty happy with how this came out. So code's available. You can ask me questions. And I hope that I hope it was worth it. I hope that this actually gives you some useful information that you can benefit from. Whether even if it's just using that cool library, or actually using principal component analysis or normalization, all of those important concepts, or just the fact that don't forget to check your code. And don't forget to add parentheses in your divisions so that order of operations don't screw you over. So yeah, but all right, that's it. That's all I have. Thank you again for watching. If you are here after 3 hours, then I congratulate you. I guess we won't hit the 3-hour mark, but that's probably a good thing. So, all right then. Until next time, thank you for watching, and take care.